Look at the moon long enough, and the question feels almost childish. The moon is round, the sun is round, planets round themselves, stars do the same. Drops of water gather into spheres, even black holes, in their simplest form, erase asymmetry with frightening efficiency. So why not the universe? Why, on the largest scales we can measure, does reality appear almost perfectly flat? That sounds like a contradiction. It feels like one immediately. Gravity seems to favor roundness. Nature seems to sand roughness down into curves. And yet, cosmologists keep telling us that space is flat, not smooth in some vague poetic sense, but flat in a severe mathematical one. For most people, those two ideas collide on contact. Because the moment we hear the word shape, the mind does something automatic. It reaches for objects, a ball, a sheet, a dome, a shell. It assumes the universe must be one more thing with an outer surface, one more body sitting somewhere, one more large object waiting to be imagined from the outside. And that is the mistake. The real reason this question is hard is not that cosmology is too abstract. It is that ordinary intuition is using the wrong category. A planet is an object in space. A star is an object in space. A droplet is an object in space. Each one can gather itself, settle, distort, spin, collapse. Each one can take on a shape because each one exists inside a larger arena. The universe is not that kind of thing. It does not sit in some bigger room, slowly pulling itself into a neater form. It is not a giant celestial bowling ball suspended in a hidden darkness. It is not a sphere we have failed to see from far enough away. And once that sinks in, the contradiction begins to loosen. Gravity does make things round, but it makes matter round inside space. That is not a small distinction. It is the entire subject. A planet becomes round because its own gravity pulls its mass inward from every direction. Given enough mass, enough heat, enough time, mountains sink, jaggedness softens. Material flows toward an equilibrium shape. Pressure pushes outward. Gravity pushes inward. The result is not perfect, but it leans toward the sphere because a sphere is what happens when matter has somewhere to fall. Roundness is what matter does when it can relax under its own weight. But the universe, taken as a whole, is not a lump of matter sitting inside an external container. There is no outside center for everything to fall toward, no exterior direction in which the cosmos is trying to smooth itself, no cosmic hand turning a rough object into a polished one. So, when cosmologists say the universe is flat, they are not saying it looks like a sheet of paper. They are saying something far stranger. They are saying that if you measure the large-scale geometry of space itself, the rules by which distance, angle, and direction behave across the universe, that geometry appears to be extremely close to Euclidean, the old geometry of schoolrooms, the one where parallel lines stay parallel, the one where a triangle's angles add to 180 degrees, the one that feels so ordinary we mistake it for common sense. Flatness, in cosmology, is not a visual description. It is a rule for how space works. And that is where the question stops being easy. Because now the problem is no longer, why didn't the universe become a ball? Now the problem becomes much sharper, much more interesting, much less forgiving. Why does space itself seem balanced on the knife edge between different possible geometries? Why does the universe appear so close to the critical density that separates one cosmic fate from another? Why, in a reality that could in principle be positively curved like the surface of a sphere, or negatively curved like a saddle, do we seem to inhabit one that comes out almost exactly flat? That is not a cosmetic feature. It is one of the deepest clues we have about the early universe. And it gets stranger still. The things that feel most persuasive to the eye, round planets, round stars, even the soft curvature of horizons, are not evidence against flatness at all. They are local events, small-scale consequences of gravity compressing matter, heat redistributing pressure, rotation bulging the equator, collapse erasing roughness. They happen inside the universe. They tell you almost nothing about the geometry of the universe as a whole. A world can be round inside a flat cosmos. A black hole can bend space-time brutally in its neighborhood, while the average large-scale geometry of the universe remains flat. A galaxy can curl, collide, warp, and shear inside a background whose global curvature is still effectively zero. That is the first real rupture this topic demands. Roundness and flatness are not opponents here. They belong to different layers of reality. One describes what matter tends to do locally when gravity is allowed to sculpt it. The other describes the large-scale geometry of space, the stage on which all of that sculpting happens. And once those two layers separate in the mind, the night sky changes. The moon stops being an argument. So does the sun. So does every sphere we have ever touched. Because none of them answer the real question. The real question is how you measure the shape of something you can never step outside of. How do you tell whether space is curved when you are trapped inside it? How do you determine whether the universe closes back on itself, opens away forever, or rides the exact middle line between those possibilities? How do you discover the geometry of the room when the room is all there is? Human intuition is not naturally built for that. Vision wants an outside view. It wants edges, silhouettes, contours against a background. It wants to look at the universe the way it looks at an orange. But cosmology became powerful only when it gave up that urge. Because curvature does not need an outside observer to exist. Geometry can reveal itself from within. Imagine a tiny creature living on a vast surface, too large for its curvature to be obvious. It cannot rise above that surface and look down on it. It cannot step off the world and inspect the whole shape. But it can still measure. It can draw giant triangles. It can compare the paths of light. It can ask whether parallel routes remain parallel, or whether they slowly drift together or apart. In other words, it can let geometry betray itself. That is what cosmologists learned to do. They stopped asking what the universe looks like from nowhere, because that question has no operational meaning, and they started asking how distance behaves inside the only space we can inhabit. That shift is subtle, but it changes everything. Because once shape stops meaning outline and starts meaning geometry, the universe becomes less like an object and more like a law, less like a thing with a surface and more like a structure with measurable rules. The question becomes harder to picture, but easier to state precisely. And precision is where the real unease begins. Because a flat universe is not merely one possible option among many. In ordinary cosmology, it is a kind of unstable balance, too much density, and space curves one way, too little, and it curves another, exactly the right amount, and large-scale space lands on the middle line. That sounds innocent until you realize how exact that middle line seems to be. Not approximately, not loosely, astonishingly. The more carefully we measure, the more the visible universe appears to sit perilously close to that balance point, close enough that physicists were forced to ask whether this could really be an accident at all. So the question we began with is already changing shape. At first it sounded visual. If gravity likes spheres, why isn't the universe round? But that was the child version of the question, the eyes version, the version built from apples, marbles, moons. The adult version is colder. Why does space itself appear so nearly uncurved? Why is the large-scale geometry of the universe so eerily close to perfect balance? And what happened in the earliest moments of cosmic history that made that balance possible in the first place? Because this is where the topic stops being about shape in the ordinary sense. This is where it becomes a story about geometry, measurement, and a universe that may have begun so violently that any original curvature was stretched almost beyond detection. The moon was only bait. The real mystery was never why worlds become round. The real mystery is why the space between them does not. Because once you see that distinction clearly, the old intuition starts to look almost embarrassingly local. Gravity rounds planets because planets are finite collections of matter. They have a center of mass. They have material that can move, deform, settle, fracture, melt, cool. A young world begins rough, violent, unfinished. It is struck, torn open, heated from within. Rock rises, metal sinks, crust buckles. But if that world is large enough, gravity keeps applying the same instruction from every direction at once. Fall inward, not metaphorically, physically, relentlessly. A mountain is not just a shape, It is a structure temporarily resisting collapse. A ridge is matter holding itself above the equipotential surface gravity would prefer. On a small asteroid, rock can keep its defiance. Gravity is too weak to force obedience. You can get lumpy worlds, bent worlds, objects that look less like planets than debris frozen in strange postures. But cross a certain threshold of size, and self-gravity becomes tyrannical. Stone behaves less like architecture and more like burden. Peaks slump, interiors differentiate. Matter begins, however slowly, to flow toward the shape that minimizes energy. That shape is almost a sphere, not because the universe loves circles in some mystical way, not because roundness is a cosmic aesthetic preference, because if every part of an object is being pulled toward the center, then the configuration that distributes that pull most evenly is the one where no direction is privileged. Equal distance from the center, equal pressure in every direction. A sphere is not decoration, it is a settlement. A star obeys this even more brutally. A planet can keep scars. A star barely gets the chance. In a star, pressure and gravity are locked in an argument violent enough to produce light. Gravity tries to crush the whole structure inward. Thermal pressure from nuclear fusion pushes back outward. The result is not static peace, but a continuous balance under enormous stress. Every second, the star is trying to fall. Every second, the reactions in its core answer that fall with outward force. The reason the star remains nearly spherical is the same reason a drop of water beads up or a soap bubble closes on itself. Uniform forces, applied through the whole body, erase asymmetry wherever they can. Roundness, here, is a signature of confinement. Matter is free to move, so it moves into obedience. That idea feels simple enough when the object is tangible. You can hold a pebble. You can watch molten glass gather under surface tension. You can picture a hot young planet smoothing under its own weight. But even there, reality is a little less neat than intuition wants. Rotation complicates everything. Spin introduces favoritism. An equator bulges. The poles flatten slightly. Jupiter is not a perfect sphere. Neither is Earth. Neither is the Sun. Local geology, magnetic fields, turbulence, crust, collisions, all of these leave fingerprints. Nature does not generate perfect geometry. It generates pressured approximations. That matters because it already hints at the deeper truth. Even when gravity makes things round, it is not producing some abstract shape in a vacuum. It is acting on matter under specific conditions, inside a pre-existing geometry, through local dynamics. The sphere is not a universal commandment. It is the outcome of a certain kind of physical problem. And that problem is not the one the universe is solving. The universe is not one more self-gravitating ball with enough time to relax. That is where the ordinary mental image fails. It quietly sneaks in an outside point of view. It imagines all the galaxies, all the matter, all the radiation, all the dark matter, all the empty reaches between them, bundled together as though they formed a giant object sitting inside some larger emptiness. Then it asks why that object is not spherical. But what exactly would that sphere be a sphere in? Where would its outer surface be? What would lie beyond it? What would its center be measured relative to? Questions like that feel natural, only because human perception evolved in a world of bounded things. Stones have edges, lakes have shores, bodies occupy locations inside larger bodies of space. So, when we hear the universe, the old machinery of perception tries to do what it always does, shrink the totality of reality into the category of object. Yet cosmology becomes serious only when that habit is stripped away. Because the universe, in the sense relevant here, is not an object embedded in a higher visible arena. It is the total space-time structure in which embedded objects appear. Galaxies are in it, clusters are in it, radiation moves through it, distances are defined by it, expansion belongs to it. The word universe is already pointing at the stage, not another actor standing on the stage. And that changes what shape can even mean. When you ask for the shape of an apple, you mean its boundary, its outer contour, the set of points where the apple ends and the surrounding air begins. But When you ask for the shape of the universe, there may be no meaningful outer contour at all. No outside air, no larger box, no external camera angle from which the whole thing reveals a silhouette. So, the old image of a cosmic globe is not just unhelpful, it is conceptually incoherent. This is why cosmologists had to learn a colder language. Not the language of outline, but the language of geometry. Not, what does the universe look like from the outside? But, what rules does space obey from the inside? That shift sounds subtle until you feel its consequences. Because a space can be curved without curving into anything we can picture, it can possess intrinsic geometry. Distances can behave differently. The sum of angles can change. Parallel trajectories can converge or diverge. A straight line, followed faithfully enough, might carry you through a geometry whose global behavior is not Euclidean, even if no edge ever appears in front of you. Human intuition resists this because it wants curvature to be visual. It wants a sheet bent upward, a ball seen from afar, a surface warped into some surrounding dimension. Those images are useful as training wheels, but they can mislead. The deep point is not that space bends like rubber in a larger room. The deep point is that geometry can be different on its own terms. A creature trapped on an enormous two-dimensional world would not need to leave that world to discover its curvature. It could draw a huge triangle and measure its angles. It could send out two initially parallel travelers and see whether they drift together. It could compare the circumference of a great circle to its radius and notice a mismatch with Euclid. Every one of those measurements would be internal. No godlike aerial view required. Curvature can announce itself from within. And once you understand that, the phrase "the universe is flat" becomes less poetic and more severe. It stops sounding like an image and starts sounding like a measurable claim about relationships. It means that, on the largest scales accessible to us, space behaves as though Euclid still has jurisdiction. Straight paths do not reveal a detectable global bend. Triangles do not show the excess or deficit you would expect from large positive or negative curvature. The architecture of distance does not seem to close in on itself or flare outward beyond the flat case. That is already strange enough. But it gets more delicate. Because in general relativity, gravity is not just a force acting inside an inert stage. Matter and energy affect space-time itself. Mass tells geometry how to curve. Geometry tells matter how to move. Locally, around stars, galaxies, and black holes. This produces real curvature, not metaphorical curvature, not visual flourish, but physical distortion of trajectories, time intervals, and spatial relations. Light bends, clocks disagree, paths that would have been straight in empty flat space-time become impossible. So now another confusion becomes tempting. If gravity bends space-time, and the universe contains matter everywhere, why would the universe as a whole not simply end up curved in the same way that local space-time does around massive objects? Because local curvature and global spatial curvature are not the same claim. That distinction is one of the most important in the whole subject. A flat universe, in the cosmological sense, does not mean every region is perfectly unwarped. It does not mean black holes stop existing. It does not mean galaxies fail to lens light, or that stars do not create gravitational wells, or that space-time is featureless and calm. It means that if you smooth over the local clutter, average over the stars, the voids, the clusters, the violent asymmetries, the large-scale spatial geometry comes out astonishingly close to the flat case. Like an ocean viewed from orbit. Stand inside it, and nothing is simple. Waves rise, storm fronts tear across the surface, trenches fall away into darkness, currents twist, foam explodes into white violence. But from far enough back, averaged over enough chaos, the sea can still define a level. That is closer to what cosmologists mean. The universe is full of local drama. Matter collapses, stars ignite, galaxies collide, black holes excavate space-time with savage precision. None of that automatically decides the global geometry. Those are events within the cosmos. Flatness is a claim about the large-scale background structure against which those events unfold. And once that lands, the original question begins to mature. Not, why is the universe flat when everything else is round? But why did we ever think those were rival descriptions in the first place? Roundness belongs to local matter, finding equilibrium under gravity. Flatness belongs to large-scale space obeying a particular geometric rule. One is about objects settling. The other is about the architecture that lets objects exist. And architecture is not inferred by staring at the furniture. Which is why the moon, for all its cold authority, cannot answer the question it seemed to pose. Neither can the sun, neither can Jupiter's swollen equator, or the near-perfect sphere of a quiet star. They only tell us that gravity knows how to discipline matter. They do not tell us whether space itself closes, opens, or rides the middle line between those possibilities. To answer that, we need something larger than any planet and older than any star. We need a ruler big enough to test geometry itself. And the strange elegance of cosmology is that such a ruler exists, not carved from metal, not held in any hand, but frozen into the oldest light the universe still allows us to see. That light has been traveling toward us for almost the entire age of the universe. Long before there were planets, long before stars had filled galaxies with heavy elements, long before anything existed that could look up and wonder what kind of place it was living in, the universe was a hot, dense plasma, bright, opaque, and violent enough that light could not move freely for more than an instant. Space was filled with charged particles. Electrons scattered photons constantly. Every direction was glare. Every path was interrupted. The young cosmos was not dark. It was too bright to see through. Then, after hundreds of thousands of years of expansion and cooling, something delicate happened. The universe became transparent. Electrons joined nuclei to form neutral atoms. Scattering dropped catastrophically. Light, no longer trapped in that searing fog, began to stream outward across space. Some of those photons are still arriving now, stretched by cosmic expansion into microwaves, faint and cold, but still carrying the imprint of the universe when it was almost unimaginably young. This is the cosmic microwave background. Not a symbol, not a theory artifact, actual ancient light, a fossil surface of visibility. And hidden inside it is one of the strangest measuring devices ever discovered. Because the early universe was not perfectly smooth, it was close to smooth, astonishingly close, but not exact. Tiny fluctuations in density and temperature moved through that primordial plasma like sound waves through air. Regions of compression and rarefaction formed and evolved. Matter tried to fall inward under gravity. Radiation pushed outward. The result was a kind of cosmic ringing, an enormous oscillation written into the infant universe before light finally decoupled and carried that pattern away. What matters is that those oscillations had a characteristic size, a real physical scale. A maximum distance sound waves in the early plasma could travel before the universe became transparent. That distance became frozen into the background radiation like a fossilized ruler. And once you possess a known ruler in the early universe, geometry stops being abstract. Because geometry decides how big that ruler appears to us now. This is the move that gives cosmology its cold authority. We do not leave the universe and inspect its shape from outside. We let the universe measure itself. We compare known physical scales to observed angular sizes on the sky. We ask a geometric question in the only form science will tolerate. What would this ancient ruler look like in a flat universe, in a positively curved universe, and in a negatively curved one? If space is positively curved, the large-scale analog of spherical geometry, then light paths converge relative to the flat case, and that ruler appears larger on the sky. If space is negatively curved, more saddle-like, more open, light paths diverge, and the same ruler appears smaller. In a flat universe, it lands at a particular angular size. So, the microwave background becomes something almost eerie. A relic glow from the early universe, used not merely to reconstruct the past, but to test the geometry of the whole arena. And when cosmologists made that measurement carefully, the result was severe. The ruler landed where flatness said it should. Not with infinite certainty. Science does not offer that kind of theatrical closure, but with enough precision to force a conclusion that changed modern cosmology. On the largest scales we can meaningfully observe, the universe is extremely close to spatially flat. It is hard to overstate how strange that is. Because flatness, when phrased casually, sounds like a default, a bland outcome, the absence of something interesting. But in cosmology, it is not bland at all. It is the knife-edge case, the exact middle option. Too much total density, and space bends one way. Too little, and it bends the other. Flatness is the boundary between those two behaviors. And boundaries in physics are rarely where intuition expects nature to settle. This is where the word density enters the story, and with it, a more precise version of the question. The shape of space is tied to how much matter and energy the universe contains. Not just the visible part, not just stars and glowing gas and galaxies, but the total cosmic budget, ordinary matter, dark matter, radiation, dark energy, everything that contributes to the large-scale dynamics of expansion. General relativity connects that content to geometry through the Friedmann equations, the mathematical backbone of modern cosmology. Out of that framework comes a special value, the critical density. It is called critical for a reason. This is the density at which large-scale space comes out flat, higher than that, and space has positive curvature, lower, and it has negative curvature, exactly equal, and the geometry rides the middle line. That sounds almost too neat, as though the universe were answering a multiple-choice question with suspicious elegance. But the elegance is real. The geometry of space is not being guessed from appearances. It emerges from the relation between expansion and total density. Cosmology asks, in effect, how fast is the universe expanding? How much gravitating stuff does it contain? And what geometry makes those facts consistent with general relativity? The answer, to extraordinary accuracy, is the flat case. Yet this answer produces a deeper discomfort the moment you look backward in time. Because the more you rewind the universe, the more delicate that balance seems to become. A universe that is close to flat today had to be incredibly close to flat in its infancy. Not casually close, not within some forgiving margin. The deviation from the critical case had to be fantastically tiny very early on. Otherwise, as the universe evolved, that deviation would have grown. Positive curvature would have become dominant, or negative curvature would have. The middle line would have been lost. This is the flatness problem. And despite the calmness of the phrase, it is one of the most unsettling clues in cosmology. At first, flatness looked like a measurement. Then it became a balance. Now it starts to look like a demand for explanation. Why was the early universe so absurdly well tuned to the critical case? Why did it begin so close to the boundary between different geometries? Why was the total energy density set with such shocking precision that, billions of years later, space still appears nearly flat? That is when flatness stops sounding ordinary and starts sounding improbable. Imagine balancing a pencil on its tip in a shaking room. For an instant, the image feels impossible, not because the pencil cannot, in principle, occupy that position, but because any tiny error will grow, any tiny lean becomes a fall. Now, imagine discovering a pencil that has somehow remained balanced through cosmic history, surviving expansion, cooling, structure formation, the birth of stars, the assembly of galaxies, and the emergence of observers capable of noticing the trick. That is not a perfect analogy, but it captures the pressure. Flatness is not puzzling, because flat space is visually strange. It is puzzling because near flatness appears dynamically fragile. And once that fragility is visible, the old question about round things becomes almost quaint. Of course planets are round. They are local systems finding equilibrium. The real mystery is why the large-scale geometry of the universe appears to have been prepared with such precision that curvature never had the chance to dominate. That is the point at which the story stops being about what we see and becomes a story about what had to be true before anything visible existed. Before stars, before galaxies, before atoms, before the oldest light broke free. Something in the early universe either set this balance with extraordinary exactness or drove the universe toward flatness so violently that any earlier curvature was diluted almost beyond measure. That second possibility will become the hinge on which the whole subject turns. Because if flatness is not a coincidence, then it may be the scar of an event so extreme that it changed not just what the universe contains, but the geometry of the space those contents live in. And that means the microwave background did more than reveal a number. It exposed a wound. A universe this flat was not merely born quiet. It may have been flattened. Flattened by what? That is where the story becomes less intuitive than the original question ever was. Because once cosmologists understood how delicate flatness really is, they ran into a brutal choice. Either the early universe began with an almost absurdly precise balance, so precise that even an unimaginably small departure from the critical density would have destroyed the near-flat cosmos we now observe, or some later process forced the universe toward flatness, whether it began that way or not. The first option was not impossible. Physics permits initial conditions, but as an explanation, it felt thin. It simply moved the mystery backward and made it sharper. Why should the primordial universe have been tuned so exquisitely? Why should the total density have landed so close to the critical value in the first place? Why should the geometry of space have begun in such a precarious state, balanced so perfectly that billions of years of cosmic evolution never managed to pull it decisively toward positive or negative curvature? This was not the kind of question you answer by admiring the data. It was the kind that demands a mechanism. And the mechanism that emerged was one of the most violent ideas in modern physics. Inflation. Not the slow, familiar inflation of prices or swollen stars. Cosmological inflation means a brief era in the very early universe during which space expanded at an astonishing, almost grotesque rate. Not matter rushing outward through a pre-existing emptiness. Space itself expanding so quickly that distances doubled, then doubled again, then doubled again, with a relentless speed that strains ordinary language. This is one of those moments where the mind tries to protect itself with metaphor and usually chooses the wrong one. People hear expansion and picture an explosion, debris flying outward from a center into surrounding space, a blast, a fireball. But inflation is stranger than that, because there may be no meaningful external space for the universe to explode into. The distances inside the universe change. The geometry itself stretches. And when geometry stretches fast enough, something remarkable happens. Curvature fades. This is the hinge. A positively curved space, if expanded violently enough, becomes harder and harder to distinguish from flatness within any finite observable patch. The same is true, in a different way, for negative curvature. Expand the scale hard enough, and any original bend is driven outward, diluted, made observationally negligible. Local irregularities do not disappear, but large-scale curvature gets crushed beneath the sheer growth of space. It is like being trapped on the surface of an immense world. If that world is small, its curvature reveals itself quickly. Walk far enough, and geometry betrays the shape. But if the world swells to almost inconceivable size, the patch you can explore begins to look flatter and flatter. Not because the surface stopped being curved in some absolute metaphysical sense, but because the radius of curvature became so vast that, within your horizon, Euclid regained the appearance of truth. That analogy is imperfect, but useful. Inflation does not politely adjust the universe. It overwhelms it. It takes whatever curvature may have existed and stretches space so ferociously that the observable region is driven toward flatness. The critical density stops looking like a miraculous fine-tuning and starts looking like the natural aftermath of a specific early event. The universe appears balanced because inflation made imbalance hard to see. That is why inflation mattered so much when it was proposed, not because it was a flashy addition to cosmology, because it turned a disturbing coincidence into an intelligible consequence. And flatness was only part of the appeal. The early universe posed more than one humiliating question. One of them was the horizon problem, distant regions of the cosmos, separated so widely that light could never have traveled between them in ordinary expansion, nevertheless show nearly identical temperatures in the microwave background. Why should places that never exchanged information look so eerily alike? Inflation offered an answer. Before the violent expansion, those regions may have been much closer together, close enough to come into thermal equilibrium. Inflation then tore them apart so fast that they became causally isolated long after their properties had already been synchronized. In other words, inflation did not solve just one puzzle. It solved several at once. And that is usually where an idea becomes dangerous in science, when it begins to explain more than the question that first summoned it. Still, the flatness problem remains one of its cleanest victories. Without inflation, the early universe had to begin balanced with almost painful exactness. With inflation, flatness becomes less like a gift and more like fallout. The expansion drives the density parameter toward 1. The curvature term becomes less and less important. Space, within the observable patch, is forced toward the middle line. Not because the universe preferred elegance, because inflation was ruthless. The phrase can sound abstract, so it helps to feel what is being claimed. Imagine an irregular mark drawn on a rubber surface. Now, stretch that surface not gently, but exponentially. Faster than the mark can matter, faster than the eye can keep scale. What once looked bent begins to look straight across any small surviving patch. The larger the stretch, the less visible the original irregularity becomes. Inflation is not literally a rubber sheet. Space is not a classroom prop. But the intuition survives. Violent stretching punishes curvature. That gives flatness a new emotional tone. Before inflation, near flatness felt unnervingly delicate, as though the universe had been balanced by a hand we could not see. After inflation, near flatness feels more like aftermath, the relic condition left behind by an extreme event in the first fractions of a second. The visible universe does not appear flat because cosmic geometry was born tame. It appears flat because whatever earlier bend existed may have been pulled outward beyond our ability to detect it. That distinction matters, because inflation does not necessarily prove that the entire universe, in the ultimate global sense, is exactly flat. It tells us something more operational and, in a way, more unsettling. The part we can observe has been stretched so close to flatness that any residual curvature is now tiny compared with our measurable horizon. That is a weaker statement than popular language often implies, but also a more honest one. Cosmology deals in horizons, in limits, in what can be inferred from within a finite visible patch. The observable universe is not automatically the whole universe. It is the region from which light has had time to reach us since the hot beginning. Beyond that lies not necessarily nothing, but unobserved continuation, perhaps more of the same. Perhaps a larger geometry whose true global properties exceed anything we can presently test. So, when we say the universe is flat, scientific honesty requires a slight tightening of the sentence. We mean that the observable universe is consistent with extremely small spatial curvature, close enough to flat that the flat model describes large-scale geometry extraordinarily well. That is not verbal caution for its own sake. It is part of the truth. Because inflation explains why our patch should look this way, even if the whole cosmos, on scales vastly beyond observation, is not exactly flat in some ultimate sense. It may be, it may not be. The measurements tell us what we can responsibly say about the region accessible to evidence. And even that limited statement is astonishing. It means the sky itself may be carrying the residue of an event so violent that it rewrote the apparent geometry of existence. The worlds we inhabit, the stars we map, the galaxies we count, all of them arose inside a space-time background that may have been leveled by expansion before structure had the chance to form. The universe did not begin as the calm stage we now imagine. It may have become calm by surviving something almost inconceivably extreme. And once that possibility is allowed in, another misconception has to die. Flat does not mean simple. Flat does not mean empty. Flat does not mean nothing happens there. A universe can be globally near flat and still be full of local wounds, cliffs, wells, turbulence, collapse, heat, violence, and asymmetry. In fact, the visible richness of cosmic structure had to arise inside that near-flat background. Which means the real challenge now is no longer understanding how flatness became possible. It is understanding how a universe flattened so early still went on to produce stars, galaxies, black holes, and every round thing that first misled the eye. Because flatness, by itself, is almost misleadingly serene. The word sounds smooth, quiet, empty. It suggests a cosmos with no drama in it, no texture, no structure, no places where gravity can dig its fingers in. But that impression only survives if we keep confusing large-scale geometry with local conditions. And by this point, that confusion has become the central thing the script is trying to dissolve. A universe can be globally near flat and still be locally ferocious. That is not a loophole. It is exactly what general relativity allows. The large-scale geometry of the universe tells you how space behaves when you average over enormous distances so large that galaxies become grains. Clusters become statistical roughness, and the bright architecture of the sky dissolves into a broad cosmic background. At that scale, the universe appears extraordinarily uniform. Matter is spread almost evenly when viewed in bulk. The Friedmann-Lemaitre-Robertson-Walker model becomes a good approximation. The equations simplify. Curvature reduces to a large-scale property of the spatial slices themselves. But no one lives at that scale. No star forms there. No planet cools there. No black hole feeds there. No life appears there. Everything vivid happens in the deviations. That is one of the most beautiful tensions in cosmology. On the largest scales, the universe is almost offensively simple, nearly homogeneous, nearly isotropic, nearly flat. And yet the world we actually inhabit is made of the tiny departures from that simplicity. The places where matter was ever so slightly denser than average. The places where gravity had something to amplify. The places where a smooth universe allowed itself the smallest imperfections and then spent billions of years letting those imperfections grow teeth. So flatness was never the enemy of structure. It was the stage on which structure became legible. This is where the early universe has to be imagined with unusual discipline, because ordinary visual language tempts us into the wrong story again. We picture a blank, smooth emptiness and then ask how anything could possibly emerge from it. But the early cosmos was not empty. It was dense beyond ordinary intuition, hot enough to dissolve atoms, flooded with radiation, saturated with matter and energy in forms far more uniform than they would later become. The reason it looks smooth in retrospect is not because nothing was there, but because the variations were tiny. Tiny is not the same as absent. And gravity is patient. If one region begins just slightly denser than another, it exerts slightly more gravitational pull. It gathers more matter. That extra matter deepens the pull further. The difference feeds on itself, slowly at first, then with growing authority. Over vast stretches of time, the small irregularities in the early universe become the scaffolding of later structure. Gas falls into dark matter, potential wells. Clouds cool, stars ignite, galaxies assemble, clusters bind, filaments emerge, voids empty out. The universe becomes textured not because the large-scale geometry failed to be flat, but because local differences inside that near-flat background were given time to amplify. That point matters enough to state cleanly. Flatness governs the broad geometry of space. Structure comes from perturbations inside the geometry. The two ideas do not compete, they interlock. And in fact, inflation itself helps explain both. Because the same inflationary expansion that drives the observable universe toward flatness also provides a way to understand the origin of the tiny primordial fluctuations from which later structure grew. Quantum fluctuations, minute, unavoidable irregularities in fields during the inflationary era, can be stretched to astrophysical scales by the rapid expansion of space. What begins as microscopic uncertainty becomes macroscopic seed. Inflation smooths the cosmos dramatically, but not perfectly. It leaves behind the faint grain, the slight unevenness, the tiny statistical wrinkles that gravity will later read as instructions. This is one of the strangest things modern cosmology has ever suggested. The galaxies may owe their existence, at least in part, to quantum fluctuations enlarged by inflation. The largest structures in the visible universe may descend from tiny tremors in the earliest fractions of a second. That is not poetry. It is the extraordinary physical logic of the model. Still, structure does not simply appear because fluctuations exist. The The universe has to let them grow. And here another ingredient enters with brutal importance: dark matter. Ordinary matter, the matter of atoms, stars, gas, planets, bodies, was tightly coupled to radiation in the early universe. Before recombination, photons scattered constantly off free electrons, and that pressure resisted collapse. Baryonic matter could not simply fall inward wherever gravity invited it. It was tangled in the glare. Dark matter was different. It did not interact strongly with light. It did not remain trapped in that radiant pressure the way ordinary matter did. So, while the visible universe was still a plasma, dark matter could begin gathering into gravitational wells. It could start building the invisible scaffolding long before atoms had the freedom to clump efficiently. That invisible scaffolding changed everything. Once the universe cooled and neutral atoms formed, ordinary matter could finally fall more effectively into the wells. Dark matter had already prepared. Gas collected, compression raised temperatures, nuclear fusion switched on. The first stars ignited. Galaxies began not as isolated miracles, but as matter responding to a hidden architecture already laid beneath the luminous universe. So, when we look at the cosmic web now, the vast filamentary distribution of galaxies across space, with clusters like knots and voids like hollow chambers, we are not seeing a contradiction to flatness. We are seeing what gravity does inside a nearly flat expanding universe, seeded with tiny primordial irregularities. Flatness did not erase drama. It made coherent drama possible. Imagine an ocean whose average level is astonishingly even across a planetary scale. That broad level does not prevent storms. It does not prevent vortices, currents, pressure fronts, violent weather, or towering waves. In a sense, it is the condition that allows those local events to be meaningfully described against a stable background. Cosmological flatness is something like that. It is not the absence of structure. It is the broad geometric baseline within which structure can emerge, evolve, and be measured. And the richness of that later structure can become extreme. A star forms when gravity compresses a cloud until its core reaches temperatures high enough for fusion. A planet becomes round when enough mass gathers for self-gravity to dominate over material rigidity. A galaxy becomes a long-lived dynamical system of stars, gas, dust, dark matter, magnetic fields, and mergers. A black hole forms when collapse crosses a line beyond which not even light escapes. None of this requires the global universe to be positively curved. None of this argues for a spherical cosmos. These are local solutions to local conditions, unfolding inside the broader space-time background. Which is why the original question now begins to sound not merely naive, but instructive. Why is the universe flat when everything else is round? Because everything else was never everything else. It was a list of local objects, things made of matter, things with centers, things capable of settling under force, things with boundaries. The universe, in the cosmological sense, is not one more member of that list. It is the framework in which the list exists. Gravity made worlds round because worlds can collapse. It did not make the universe round because the universe was never a world. That line lands harder now because we have earned it. We have already separated local shape from global geometry. We have already seen how flatness is measured. We have already seen why it is dynamically strange and why inflation offers relief. Now, we can add the final correction. Flatness does not sterilize reality. It coexists with local curvature, local collapse, local asymmetry, local violence. In fact, without those local departures, the universe would remain almost unreadably bland. The microwave background itself shows this balance beautifully. On one hand, it is astonishingly uniform, nearly the same temperature in every direction, evidence of a cosmos smooth on large scales. On the other, its tiny anisotropies reveal the fluctuations from which everything structured would later emerge. Uniformity and imperfection, flatness and seed, calm geometry and latent drama. The whole later universe is hidden in that tension. That is what makes the subject feel so severe. Reality is not built according to the preferences of human visualization. It permits large-scale simplicity and small-scale violence at the same time. It permits a universe whose average spatial curvature is nearly zero, while stars distort space-time locally, and galaxies grow from gravitational instability. It permits local roundness without global roundness, because those statements belong to different levels of description. And once that becomes clear, a deeper question begins to surface. If the universe is so nearly flat, and if inflation helps explain why, then how certain are we really? How much of this is inference? How much is measurement? And how directly has the sky itself told us that Euclid survives on cosmic scales? Because eventually every elegant argument has to face the data. And in this story, the data came not from a single star or galaxy, but from the oldest pattern of light in existence, a faint temperature map across the sky that carried, in almost invisible variations, the geometry of the universe written into angle. That pattern is so faint that, if the universe were translated into ordinary sensory scale, most of us would miss it completely. The cosmic microwave background is almost uniform. Its temperature varies across the sky by only tiny fractions, minute fluctuations laid over an otherwise astonishingly smooth glow. And yet, those tiny fluctuations became one of the most powerful pieces of evidence in modern science, because they do not merely tell us that the early universe had structure in embryo. They tell us how geometry itself handles light across cosmic distance. To understand why, it helps to hold on to one idea with absolute precision. Geometry changes appearance. The same physical object, placed at the same physical distance, can seem larger or smaller depending on the curvature of the space through which its light reaches you. This is not a trick of bad optics. It is a property of the arena itself. In positively curved space, light paths behave differently than they do in flat space. In negatively curved space, differently again. A ruler of known size becomes a test of the geometry it lives in. Cosmology found such a ruler in the early universe. That ruler was not built by hand. It was not discovered sitting quietly in some corner of the sky. It emerged from the physics of the primordial plasma, the same dense, luminous medium in which gravity and radiation were locked in their ancient contest. Regions that were slightly overdense tried to collapse. Radiation pressure pushed back. The result was an oscillation, a kind of pressure wave moving through the young cosmos. Like sound, but not in air. Sound in a universe before transparency. Sound in plasma. Sound before stars. These acoustic waves had a limit. There was only so much time before recombination, before the universe cooled enough for electrons to bind to nuclei and light to break free. That means there was only so far such a pressure wave could travel. The maximum distance became imprinted into the cosmic microwave background as a characteristic scale, a preferred size, a standard ruler frozen into the oldest visible light. From there, the logic becomes merciless. If the universe is positively curved, that ruler should appear relatively large on the sky. If negatively curved, relatively small. If flat, it should occupy a particular angular size. So cosmologists measured it. They mapped the microwave background in exquisite detail, first imperfectly, then better, then with enough precision to make the argument hard to escape. The pattern of hot and cold spots across the sky was decomposed into angular scales, and among those scales, one feature mattered with special force. The first acoustic peak, the signature of that primordial standard ruler. Its position told a geometric story. And the story it told was this: within the observable universe, space is astonishingly close to flat. Not vaguely, not metaphorically, numerically. That conclusion was never based on a single flourish of rhetoric. It emerged from data, from repeated refinement, from missions designed to listen to a whisper older than galaxies. COBE showed the background's fluctuations existed. WMAP sharpened the picture into precision cosmology. Planck refined it further, measuring the microwave sky with such care that the standard cosmological model became not merely plausible, but intensely constrained. Across all of that work, the same broad verdict endured. The observable universe is extremely close to spatial flatness. This is where the phrase flat universe should begin to lose all casualness. Because the sky is not offering a philosophical mood here, it is offering a measurement, a 1-degree scale relic from the early universe, translated through relativistic cosmology into a statement about the large-scale geometry of everything we can see. Ancient light became geometry made visible. And that is one of the rare moments in science when the method itself feels almost mythic, not mystical, more severe than that. The universe generated its own ruler in the first few 100,000 years, preserved it across billions of years of expansion, and delivered it to observers who did not exist when the pattern was set. We arrived absurdly late, looked up, and found that the sky had been quietly keeping records the entire time. Still, measurement in cosmology is never as clean as popular summaries pretend. The microwave background does not speak in a single isolated sentence. Its interpretation depends on a model, the expanding universe, general relativity, the contents of the cosmic energy budget, the behavior of perturbations, the role of dark matter and dark energy, the relation between physical scales and observed angles. That does not weaken the result. It situates it honestly. Science at this level is a coherent structure. Geometry, expansion, density, radiation history, and perturbation physics all interlock. The strength of the flatness inference comes partly from how well those pieces reinforce one another. It is not just that one number points toward flatness. It is that an entire model hangs together with extraordinary discipline when flatness is included. This matters because people sometimes imagine cosmology as a field built out of distant guesses, elegant, perhaps, but permanently detached from real test. Yet, flatness is exactly the kind of result that exposes how wrong that caricature is. The universe is too large to hold in the hand, but it is not too large to interrogate. If a physical scale can be identified in the early plasma, if that scale survives as an imprint, if light carries it to us, and if geometry alters its apparent angle, then the shape of cosmic space becomes measurable in principle. That principle is no longer hypothetical. We have already used it. And what it revealed was not a dramatically curved universe closing back on itself at scales just beyond a few galaxies. Not a wildly open geometry diverging into obvious hyperbolic behavior. What it revealed was a cosmos balanced so near the flat case that the residual curvature, if any exists within the observable region, is remarkably small. That word, residual, matters. Because even now, caution remains part of the truth. Observations do not compel us to say the entire universe is exactly flat in some ultimate and global sense. They compel a narrower claim. The observable universe is consistent with very small spatial curvature, close enough to flat that departures from flatness are tightly constrained. That is what the data honestly earn. And perhaps that careful phrasing feels less emotionally satisfying than a grand absolute. But in another way, it is more haunting. Because it leaves us with a universe whose visible patch is nearly perfect, while the totality beyond our horizon remains partly hidden. We can say with confidence that our cosmic neighborhood, taken on the largest scales, does not display significant spatial curvature. We cannot yet step outside the observable domain and inspect the whole of reality. The geometry beyond the horizon may continue exactly as it does here, or not. The data do not permit theatrical certainty. They permit something better. They permit disciplined wonder. And disciplined wonder has a different emotional texture from fantasy. It does not ask the universe to become stranger than evidence allows. It notices how strange the evidence already is. It notices that the oldest light in existence carries a frozen ruler. It notices that geometry can be read from temperature patterns across the sky. It notices that the verdict points toward flatness so strongly that any deviation, if present, must be subtle, and then it asks what that subtlety means. Because once the measurement is secure, the emotional pressure moves again. Flatness is no longer just a conceptual distinction between local shape and global geometry. It is no longer just a theoretical balance encoded in the Friedman equations. It is no longer just a problem in need of inflationary rescue. Now it is empirical. The sky itself has joined the argument. And when data, theory, and early universe mechanism all begin converging on the same conclusion, the question changes once more, not whether the observable universe is near flat, but what it means that reality came out this way. What kind of beginning leaves behind a cosmos so geometrically disciplined on the largest scales, and yet so fertile with local variation that stars, planets, galaxies, and black holes can still emerge within it? Because the microwave background does not show us a finished universe. It shows us a young one, a nearly smooth one, a cosmos in which all later richness still existed only as faint statistical hints. The galaxies were not there yet. The clusters were not there yet. The planets were not there yet. The round things that once misled the eye had not formed. And still, already, the geometry was written in. That is the cold elegance of the result. The universe did not wait for stars to exist before choosing the rules of distance. It did not wait for matter to assemble before deciding the large-scale relation between density and curvature, before worlds became round. Before local gravity learned how to carve the visible sky into objects, the deeper geometry had already been laid down. Flatness came first. The things we instinctively trust came later. And that means the oldest light in the universe did more than tell us what the early cosmos looked like. It told us that the stage was already set, and that every round world we would one day mistake for an argument was born inside a geometry it never had the power to define. Which is why the real mystery was never the moon. The moon only made the category error feel persuasive. It made local shape look universal. It made gravity seem like a rule about everything, when in fact it was only ever a rule about matter under specific conditions. By now that illusion has been dismantled. Round worlds are not evidence about the geometry of the cosmos. They are consequences inside it. But once that misconception falls away, a more severe tension takes its place. If the large-scale universe is so close to flat, and if the oldest light confirms it, and if inflation explains how such flatness could emerge, then flatness stops looking like a curiosity and starts looking like a structural clue. It begins to tell us something about the kind of beginning this universe had, not just what it contains now, but what sort of event may have governed its first decisive moment. Because inflation, for all its explanatory power, is not an ornamental idea. It is not the kind of theory one adds simply to make the story more dramatic. It was proposed because the universe was too disciplined in too many ways at once, too smooth across causally distant regions, too close to flat, too coherent on scales that ordinary expansion alone struggled to explain. Inflation gave cosmology a mechanism equal to that discipline. But mechanisms come with consequences. If inflation happened, then the universe we can observe is only a surviving patch of a reality that was once stretched with terrifying violence. The visible cosmos, all the galaxies we map, all the clusters, all the voids, all the microwave background, may be a small remnant of a much larger space-time whose original curvature, whatever it was, has been pulled so far outward that we no longer feel it. Flatness, then, is not just a property. It is a memory loss, a geometry erased by scale. That possibility changes the emotional atmosphere of the subject, because when people hear that inflation solves the flatness problem, it can sound as though the mystery has simply been tidied away. The difficult question arose. A clever theory answered it, and now the matter is closed. But physics is rarely that kind. An explanation does not always simplify reality. Sometimes it deepens the strangeness while making it lawful. Inflation is like that. It helps explain why the observable universe is near flat. But it also forces us to picture a beginning, unlike anything in ordinary experience. A tiny patch of space-time dominated by a form of energy that drove exponential expansion, stretching quantum-scale fluctuations to cosmic size, leveling curvature, and laying the groundwork for everything that would later become visible. If that is even approximately right, then the world we inhabit is not simply a universe that expanded. It is a universe whose most important large-scale properties were forged in a brief episode of astonishing extremity. The calmness of the night sky hides that violence well. That is one of the recurring humiliations of cosmology. What looks placid from a late vantage point often carries the residue of something brutal in its origin. The cosmic microwave background feels quiet now because it has cooled to just a few degrees above absolute zero. But it is the faded afterglow of a universe that was once incandescent. The large-scale geometry feels ordinary now because Euclidean intuition still works surprisingly well across our visible patch. But that apparent ordinariness may be the outcome of an expansion so violent that any primordial curvature was flattened almost beyond recovery. Reality often arrives late as calm. Its origins do not owe us gentleness. And yet, even here, science has to keep its honesty. Inflation is powerful, but it is not absolute closure. We do not possess a single universally confirmed microphysical model of inflation that everyone accepts in final detail. There are families of inflationary models, different candidate fields, different potentials, different refinements and tensions. The broad inflationary picture remains deeply influential because of how much it explains. But responsible cosmology does not confuse successful framework with complete completion. That uncertainty is not a weakness in the story. It is part of what makes the story real. Because the universe is not obligated to become emotionally satisfying at exactly the point where our theories become elegant. Sometimes a mechanism clarifies the broad shape of an answer while leaving the deeper origin of the mechanism itself unresolved. Inflation may explain why observable flatness is natural. It does not automatically tell us why inflation began, what selected its particular dynamics, whether it occurred once or in a larger inflating background, or whether the total global universe has a structure that our horizon forever conceals. In other words, flatness may be explained locally while remaining metaphysically unsettling. That is the kind of tension mature science often leaves behind. Not mystery in place of law, and not law in place of mystery, but a harder fusion of the two. The laws become clearer. The total picture becomes stranger. And that brings us back to the quantity underneath all of this, the total energy density of the universe relative to the critical value. This is the number that quietly decides the geometry of large-scale space. It is often packaged in a deceptively gentle symbol, omega, as though such notation could soften what it means. If omega equals 1 exactly, the spatial geometry is flat, greater than 1, positive curvature, less than 1, negative curvature. A small numerical relation becomes a statement about the structure of reality. What gives that number so much force is not just its present value, but the way it evolves. In an expanding universe without inflation, departures from the critical case do not politely remain small. They grow. The further you run the clock backward, the more precisely tuned the early universe has to be if it is still to appear near flat today. This is why the flatness problem carried so much emotional weight for cosmologists who first confronted it seriously. It was not a complaint about aesthetics. It was a quantitative expression of discomfort. The universe looked balanced in a way that ordinary evolution did not naturally preserve. Inflation changes that evolution. Instead of tiny deviations from flatness growing into dominant curvature, the inflationary era drives omega toward 1. The observable patch is herded toward flatness. What once required exquisite initial tuning becomes a dynamical outcome of rapid expansion. The miracle becomes mechanism. But even mechanism does not remove all unease. Because one way or another, the geometry we see is the relic of conditions so early that they sit near the edge of what present physics can reconstruct with confidence. By the time the microwave background forms, the key work is already done. By the time galaxies appear, it is done long ago. By the time planets become round, the argument is ancient history. Everything the eye trusts comes afterward. The geometry came first. The objects came later. The intuition was born last of all. That order matters more than it seems. Human beings did not evolve to think about intrinsic curvature. We evolved to catch falling objects, judge surfaces, navigate bounded spaces, recognize contours, infer solidity, survive among finite things. Our most natural intuitions are exquisitely tuned to middle scales, worlds, cliffs, tools, bodies, weather, trajectories, useful realities, local realities. But cosmology keeps exposing how parochial those intuitions are. We keep trying to elevate them into universal truths, and the universe keeps refusing. Matter is not solid in the way it feels. Time does not simply flow in the way it seems. Empty space is not truly empty, and shape, at the largest scale, is not what the eye thinks it is. This is what makes the flatness question so psychologically powerful. It begins with a child's objection. If gravity makes things round, why isn't the universe round too? It sounds almost innocent. Then, step by step, the question reveals that innocence to be a disguise for a deep mistake. We were importing the logic of objects into the geometry of space-time. We were asking the universe to behave like furniture inside itself. Once you see that, you cannot quite return to the old mental picture. The night sky stops looking like a collection of things inside a larger black box. It starts to feel more like local ornament, suspended within a geometry whose large-scale structure was fixed before any ornament existed. Planets and stars become late-surface details. The deeper order lies beneath them, in the way space expands, in the way ancient light crosses it, in the way total density and curvature lock together. And one of the most unsettling features of that deeper order is how indifferent it is to our preferred imagery. The universe does not care that spheres feel fundamental. It allows them where local physics generates them. It does not elevate them into the shape of reality itself. That is an important turn, because it prepares the next one. We have already separated local roundness from global geometry. We have already let the microwave background testify. We have already seen why critical density matters and why inflation relieves the flatness problem. But another misconception still lingers in the background, and it is subtler than the first. Even after people accept that the universe is not an object with an outer contour, they often imagine flatness as a kind of final simplicity, as though the phrase flat universe means cosmology has somehow reached the most ordinary possible answer. As though the geometry of space has turned out to be disappointingly plain. But near flatness is not plain at all. It is one of those cases where reality looks simple only after enormous theoretical and observational effort has taught us how difficult that simplicity actually is. It is hard-won simplicity, measured simplicity, dynamically suspicious simplicity, the kind that becomes more uncanny the longer you look at it. Because the most unnerving facts in cosmology are often the ones that sound least dramatic when stated carelessly. The observable universe is nearly flat. A sentence so quiet it almost conceals what it means. A statement about ancient balance, about inflationary violence, about the limits of our horizon, about the difference between local wound and global rule, about geometry written into the sky before the first star burned. And perhaps most of all, about the humiliating precision with which reality keeps forcing us to abandon the intuition that first felt obvious. What makes that precision so unsettling is not just that it corrects us. It corrects us at the level of category. The first mistake was visual. We treated the universe like an object and asked why it failed to resemble the objects we know. But the deeper mistake was philosophical. We assumed that what feels fundamental to human perception must also be fundamental to reality. Edges feel fundamental. Surfaces feel fundamental. Roundness feels fundamental. A thing seems real when it can be enclosed by a contour and held apart from its background. Cosmology keeps dissolving that instinct. Because the universe, at the level where flatness matters, is not primarily a thing with a contour. It is a set of geometric relations, a dynamical space-time, a rule-bound structure in which matter, radiation, and curvature interact. The deeper we go, the less reality looks like a collection of finished objects, and the more it looks like law taking temporary visible form. That is why the sentence, "the universe is flat," resists intuition so strongly. It asks the mind to move away from silhouette and toward metric, away from appearance and toward relation, away from the visible shape of things and toward the hidden rules by which distance behaves. And relation is harder to love than image. An image arrives all at once. A sphere can be pictured. A planet can be held in the mind. A horizon can be seen. But geometric flatness in cosmology is almost anti-visual. It lives in what angles do, in how light propagates, in the way large-scale triangles close or fail to close, in the balance between the expansion rate and the total energy density. It becomes visible only indirectly, through consequences. The human mind is not instinctively at home there, which is why the history of cosmology has so often been a history of disciplined humiliation. Each major step, has required giving up a picture that once felt obvious. Earth is not the center, the sun is not the center, the galaxy is not the center. Matter is not solid in the way it feels. Time is not universal in the way it seems. Empty space is not truly empty. And now, shape itself, at the largest scale, is not what the eye means by shape. This is not a side effect of science. It is one of its deepest patterns. The universe becomes more intelligible by becoming less intuitive. And nowhere is that pattern cleaner than here, because the apparent contradiction was never real. The roundness of local things and the flatness of large-scale space do not compete. The competition existed only in the human imagination, because we place two different levels of description inside the same mental box. Once that box breaks, the whole question changes tone. It stops being, why is the universe flat when everything else is round? And becomes, why did we expect local equilibrium shapes to tell us anything about global geometry at all? The answer is uncomfortable, because it exposes how provincial our thinking begins. We trust what gravity does nearby. We watch matter gather, relax, compress, and form nearly spherical bodies. Then we assume the universe must obey the same visual grammar. But gravity nearby is not the same as geometry globally. The collapse of a gas cloud into a star is not the same kind of fact as the spatial curvature of the observable universe. One is a local dynamical event. The other is a property of the background solution describing cosmic expansion. It takes training, and more than training, restraint, to keep those claims apart. This is why even good popular explanations often drift into misleading imagery. The temptation is always to make the universe picturable, to hand the viewer a sphere, a bubble, a dome, a stretched sheet, something with a contour and an edge. Those metaphors can help at first. But, left uncontrolled, they smuggle the old category error back in. They imply that the universe is a shape the way a fruit is a shape. They encourage the idea that flat and round must be visually rival answers to the same question. They are not, and by this point, the script has earned the right to say that more severely. The universe is not strangely flat in the face of spherical things. Spherical things are merely local compromises matter reaches under gravity. Flatness is a statement about the large-scale metric of space. Gravity can make planets round inside a near-flat cosmos, the way waves can rise on a calm sea, without changing the average level of the ocean itself. That analogy is still incomplete, but it carries the emotional truth. The local and the global can differ without contradiction. In fact, reality often becomes richest exactly where they do. Think of Earth. Stand on a plane and the ground looks flat. Sail far enough and curvature begins to matter. Study mountains and local roughness overwhelms the smoothness of the whole. None of those views cancels the others. They belong to different scales and different questions. Now, magnify that discipline by cosmic orders of magnitude. Locally, around stars and black holes, space-time can be curved enough to bend light into arcs, slow clocks, and trap even radiation. On much larger scales, galaxies cluster into filaments and walls. On larger scales again, those structures average out, and the universe becomes nearly homogeneous. Then the relevant question is not whether any given region contains dramatic local curvature, but whether the average large-scale spatial geometry departs significantly from flatness. That nesting of scales is one of the secret structures behind the whole subject. Human intuition tends to flatten scale into one blurred category. Cosmology survives by refusing to do that. A black hole and the observable universe are both described by general relativity, but they are not the same kind of geometric statement. A planet's roundness and a cosmological density parameter both involve gravity, but they do not answer the same question. A star can be nearly spherical because hydrostatic equilibrium drives it there. The universe can be near flat because inflation and critical density relations shape the large-scale background. Same theory, different regime, different meaning, different emotional burden. And that last part matters, because the emotional burden of cosmological flatness is not visual elegance, it is improbable order. Once you strip away the misleading image of a giant cosmic sheet, flatness ceases to sound plain. It becomes a statement about an early universe so carefully balanced, or so violently stretched, that even now, after billions of years of structure formation, the visible cosmos still carries almost no detectable large-scale curvature. That should not feel ordinary. It should feel austere. Austerity is a better word than wonder here. Wonder can become too soft, too permissive. It allows us to simply admire the result. Austerity forces the harder response. It asks what had to be true for this result to exist. It asks what kind of early conditions, what kind of inflationary episode, what kind of relation between density and expansion could leave behind a universe this geometrically disciplined. It asks what our measurements genuinely constrain and where our horizon still prevents total certainty. That mixture, clarity bounded by ignorance, is the emotional center of mature cosmology. We know more than intuition ever could have guessed, but not enough to turn the universe into a finished object in the mind. We know that the observable universe is extremely close to spatially flat. We know this from the cosmic microwave background, from the behavior of the primordial standard ruler, from the coherence of the cosmological model when its parameters are fitted to data. We know that local spherical objects do not count as evidence against this because they are products of local gravitational settling. We know that inflation gives a powerful mechanism for driving observable space toward flatness. We know that the flatness problem made such a mechanism more than decorative. And we know that the global geometry beyond our horizon may still outrun anything we can currently certify with perfect confidence. That is a lot. But it is not the kind of knowledge the nervous system finds comfortable. Comfort comes from boundaries, from completed pictures, from shapes that can be held against a background. The universe denies us all of that here. It tells us that the relevant shape is not an outline, but a relation, that the evidence is indirect but severe, that the geometry was settled before the visible ornaments of the cosmos existed, that the roundness of the moon is a late local fact with almost no authority over the shape of the whole. And perhaps that is why the subject lingers. Because beneath the technical language, curvature, critical density, inflation, acoustic peaks, there is a deeper disturbance. It is the disturbance of realizing that the world is not built out of the categories that sight offers first. The visible universe is not the primary layer of reality. The primary layer is the geometry that made visibility possible. The objects came later. The rules came first. That reversal should sit in the mind for a moment, because it quietly changes the hierarchy of what feels real. We tend to think the moon is real in one way, and equations are abstract in another. But cosmology keeps forcing the opposite pressure. The moon is local, temporary, derivative. The geometry encoded in the expansion of space and the oldest light of the universe is more fundamental, less accessible to intuition, more primary in law. Reality is not organized for human immediacy. It is organized for consistency. And consistency is exactly what the flatness story delivers. The microwave background says the observable universe is nearly flat. General relativity tells us why geometry and density are linked. The flatness problem reveals why near flatness is dynamically delicate without inflation. Inflation supplies a mechanism that can both smooth the universe and dilute curvature. Structure formation then unfolds within that near flat background, producing the stars, galaxies, planets, and black holes whose visible forms initially tempted us into the wrong question. Everything locks together. That does not mean every deeper origin has been solved. It means the visible contradiction has been dissolved so completely that it now seems almost impossible to recover the old confusion honestly. And that is usually the mark of a real shift in understanding. Not that the answer sounds impressive, but that the old question begins to look malformed. The universe is not flat when everything else is round. The universe is near flat on large scales, while some things inside it become round under local gravity. That sentence is less catchy, less dramatic, less immediately intoxicating. It is also much closer to the truth. And the truth, in this case, is already strange enough. Because once flatness is no longer mistaken for visual blandness, another implication comes forward. If the geometry of the observable universe is this close to Euclidean, then our visible cosmic patch may be only a tiny, nearly level fragment of something whose total extent we cannot see. A larger geometry may continue beyond our horizon, with a radius of curvature so vast that our entire observable domain samples only an almost perfectly straight patch, or the whole may be exactly flat, or topology may complicate the picture in ways subtler than ordinary curvature alone. The evidence does not let us say everything, but it does let us feel the scale of what remains open. And openness, here, is not ignorance in the lazy sense. It is the disciplined recognition that even a universe whose curvature is constrained by ancient light can still exceed the reach of complete visualization. We can measure the stage more precisely than intuition ever dreamed. We still cannot stand outside it. That is the next pressure point. Because eventually, the question becomes even larger than curvature. It becomes a question about what kind of thing a universe is when the only geometry we can certify belongs to a finite horizon, and the totality beyond that horizon may continue past any image the mind can stably hold. That is where cosmology becomes quietly merciless. Because by the time you understand what flat really means, you also understand what it does not give you. It does not give you an outside view. It does not give you the whole. It does not give you permission to imagine the universe as completed simply because one of its geometric properties has been tightly constrained. Flatness is a measured statement about the observable domain, a powerful one, a profound one, but still a statement made from inside a horizon. And the horizon matters. The observable universe is not the universe in the grandest possible sense. It is the region from which light has had time to reach us since the hot early phase of cosmic history. That boundary is not a wall. It is not an edge where reality stops. It is a limit imposed by finite age, finite light speed, and the expansion of space. Beyond it, there may be vastly more cosmos, perhaps more of the same large-scale geometry, perhaps a subtler global structure whose full form no observer in our location can ever directly reconstruct. That is one of the harshest conceptual turns in the whole subject. We can measure the geometry of our patch with increasing precision. We may never be able to certify the total geometry of everything. Those are not the same achievement. And once that distinction settles in, flatness becomes even stranger, because it may be telling us two different things at once. At one level, it tells us the observable universe behaves with remarkable fidelity to Euclidean spatial geometry on the largest scales we can test. That is already extraordinary. At another level, it hints that our visible domain may be far too small, relative to the total radius of curvature of the whole, for any global bend to reveal itself clearly here. In that case, our cosmic neighborhood would appear nearly flat, not because the entire universe is exactly flat in the strongest imaginable sense, but because any residual curvature is stretched across scales so enormous that our horizon samples only an almost level piece. Like standing on a vast plain cut from a much larger world. Walk a few kilometers, and the ground seems flat. Survey farther, and subtle curvature might emerge. Expand the scale far enough, and the distinction between local flatness and global curvature becomes inseparable from the limits of your reach. The Earth does not need to be flat for a field to look flat. A sphere of sufficiently large radius always punishes small observers with this Euclidean illusions. Inflation amplifies that possibility to almost absurd scale. If the early universe underwent violent exponential expansion, then any pre-existing curvature could have been diluted so severely that the observable patch became nearly flat, regardless of the global story. Our horizon would then be a geometrically disciplined remnant, not necessarily the whole truth, but the only part to which evidence grants us access. This is where responsible cosmology has to resist two temptations at once. The first is the temptation of false certainty, to say too much, to announce with theatrical confidence that the entire universe is flat in an ultimate sense because our measurements within the observable region point strongly in that direction. That language is emotionally satisfying, but it outruns what evidence strictly allows. The second is the temptation of false mystery, to imply that because we cannot certify the totality, nothing meaningful has been learned. That is equally wrong. We have learned something immense. We have learned that the observable cosmos is so close to flat that any residual large-scale spatial curvature within our measurable domain must be very small. We have learned that local round objects do not speak to this issue. We have learned that inflation makes such near flatness dynamically intelligible. We have learned that ancient light carries the record of that geometry. Clarity without excess, ignorance without collapse. That balance is part of the intellectual beauty here, because it means cosmology does not end in vagueness. It ends in a more disciplined kind of incompleteness, one that preserves force precisely because it does not pretend to omniscience. The horizon is not an embarrassment. It is one of the structural facts of our situation in the universe. It tells us what can be known from here. It also tells us what here cannot simply command. And perhaps that is why this subject keeps acquiring philosophical weight the deeper it goes. At first, why is the universe flat when everything else is round? Sounds like a complaint about appearances. Now it starts to reveal something much harder. It reveals that reality is layered in a way our instincts do not naturally respect. Local objects, local collapse, local curvature, local spherical equilibrium, all of that is real, but derivative. The geometry that governs the large-scale arena is more primary. The horizon that limits our access to the totality is more primary. Inflation, if correct, is more primary than any of the visible objects we first trust. By the time planets become round, the relevant structure is ancient. The things we touch are late. The rules they inherit are old. That hierarchy is not emotionally comfortable. It diminishes the authority of immediate sight. It tells us that what feels substantial, moons, worlds, stars, galactic spirals, may be less fundamental than the invisible geometric order within which they arose. It tells us that the most decisive facts about reality may not be the facts that look largest to the eye, but the ones written earliest into space-time itself. This is why cosmology can feel both clarifying and destabilizing at once. Clarifying, because the wrong question is dissolved. Destabilizing, because the right question is larger than the mind first wanted. What is the large-scale geometry of the observable universe? How tightly can it be constrained? What role did inflation play in producing it? How much of the total global structure can ever be inferred from inside a finite horizon? Those are not the questions of ordinary perception. They belong to a universe that has forced us beyond picturing and into measurement. And the force of that move is easy to underestimate. Human beings are accustomed to learning by looking. Vision dominates our confidence. We trust contours. We believe in surfaces. We feel that to know a thing is to stand outside it, inspect its form, and hold it in a completed image. But cosmology denies us that privilege almost everywhere that matters most. We do not stand outside the universe. We do not look down upon its total shape. We infer it from light, expansion, temperature anisotropies, and dynamical consistency. We know by relation, by trace, by internal evidence. The universe can only be read from inside. And that is why flat is such a severe word here. It is not a visual adjective attached to a cosmic object. It is the outcome of one of the most disciplined inference chains science has ever built. It means the oldest light carries a ruler. It means geometry changes angular appearance. It means total density and expansion locked together through relativity. It means the observable cosmos has remained astonishingly near the critical case. It means inflation, if the broad framework is right, may have driven our visible patch toward this condition before any structure formed. It means that the round things we first trusted were born inside a geometry they did not create and cannot overturn. By now, the opening contradiction has not merely been answered. It has been exposed as a symptom of something deeper, the urge to mistake local visible order for global truth. And that urge does not die easily. Even after all the equations, all the data, all the careful distinction between intrinsic and extrinsic curvature, many people still feel the pull of the old image. They still want the universe to be a thing in a room. They still want flatness to mean sheet-like and roundness to mean complete. They still want the cosmos to offer a final silhouette. But there may be no final silhouette available to minds like ours. There may only be internal geometry, measured with exquisite care, within a finite horizon, in a universe whose full extent exceeds the reach of our immediate imagery. That is not failure. It is the mature shape of the truth. And once you can live with that, another subtle shift happens. The phrase, The universe is flat stops sounding like an answer and starts sounding like a limit statement, a statement about how much curvature does not appear within our cosmic patch, a statement about how strongly Euclidean behavior survives on the largest observable scales, a statement about what inflation may have done to erase or dilute the bends that might once have mattered more. In other words, flatness is not the end of the story. It is the beginning of the right one. Because now the real implication comes into view. The universe did not owe us a geometry this simple seeming. It did not owe us a cosmic microwave background whose acoustic structure could be read so cleanly. It did not owe us a large-scale energy density so close to critical that the language of near flatness becomes meaningful at all. Whatever happened in the early cosmos, it left behind an arena in which large-scale geometry is astonishingly disciplined, and local structure is still free to erupt into the rich violence of stars, galaxies, black holes, and worlds. That combination is almost too elegant. Not in the cheap sense, not in the sense of a tidy design laid out for our admiration. In the colder sense, the sense that the laws are capable of generating visible complexity inside hidden order without ever needing to consult the expectations of ordinary intuition. And perhaps that is the deepest discomfort the topic leaves behind. Reality is lawful enough to be measured, strange enough to resist picturing, precise enough to constrain, large enough to outrun completion. The universe appears nearly flat where we can test it. And yet the totality beyond that testable patch may remain forever beyond any single image the mind can hold. That is the next threshold. Because once the visible contradiction has dissolved, and once flatness has been separated from local roundness, and once the horizon has been allowed to impose its limit, one question remains with unusual force. Not what the universe looks like, but what it means to live inside a reality whose deepest structure can be inferred with great precision, while the whole of that reality may never become an object of view at all. Because that is the final humiliation. Not that the universe is difficult, not that it is large, not even that it refuses the pictures we first want to draw. It is that the universe can be known with shocking precision in some ways, while remaining permanently unavailable in others. That combination is hard for the mind to tolerate. We prefer our knowledge to come packaged in completed images. We like to believe that if something is measured well enough, it should eventually become intuitively graspable, that the map, given sufficient refinement, will one day feel like the territory. Cosmology keeps denying that comfort. It offers exactness without intimacy, constraint without total possession. It lets us know what kind of geometry our observable patch obeys, while withholding the godlike view that would turn geometry back into a simple picture. And perhaps that is why the flatness question leaves such a long aftertaste. Because it begins with a child's category of understanding, shape as visible outline, and ends by revealing that the deepest structure of reality may not be outline-like at all. The most important facts about the universe may be facts about relation, scale, expansion, and horizon. Facts that cannot be held in the way a stone can be held. Facts that do not become more true just because they become more imaginable. The geometry does not care whether it can be pictured. It only cares whether it is consistent. That sounds cold, and it is. But it is also one of the reasons the subject acquires such strange beauty at the end. Because once you stop demanding a final silhouette, the universe begins to appear in a different register, not as a giant object waiting to be seen properly, not as a hidden sphere we have not yet backed away far enough to recognize, but as an internally legible structure whose deepest regularities can be extracted from traces. Ancient light, redshift, clustering, lensing, expansion history, the relic mathematics of a young plasma. The whole cosmos becomes less like a landscape and more like a sentence we are slowly learning how to parse. Not a sentence written for us, not a sentence simplified for our senses, a lawful sentence, spoken once in the beginning, still echoing through measurements. And flatness is one of its clearest grammatical features. That is why the result matters even beyond geometry itself, because it reveals a pattern that repeats across physics. The deeper the truth, the less it resembles the form in which intuition first encounters the world. Matter feels solid. Deeper down, it is mostly structured emptiness and fields. Time feels universal. Deeper down, it is bound to motion, gravity, and the geometry of space-time. The sky feels like a dome of visible things. Deeper down, it is a late local display inside a metric whose large-scale behavior was determined before any of those things existed. The visible world is not false. It is downstream. That may be the most important line in the entire subject, because it rearranges the order of authority. We tend to trust what arrives first to the senses. A round moon seems primary, a star seems primary, a planetary horizon seems primary, but cosmology forces the reverse ranking. Those are not the deepest facts, they are the later manifestations. The geometry came earlier. The inflationary history, if inflation is right, came earlier. The critical relation between density and curvature came earlier. The fossil light that still crosses the sky began its journey earlier than any visible object the naked eye finds persuasive. By the time the moon became round, the argument was already ancient. This is why local beauty can be so deceptive. A sphere feels complete. It has closure. It offers the eye an almost moral satisfaction, symmetry, unity, finish. It is easy to understand why human thought repeatedly promoted the sphere into a cosmic ideal. The sphere seems worthy of fundamental status. So, when the universe refuses to present itself as a giant spherical thing, some part of the imagination feels cheated. But the universe was never obligated to satisfy aesthetic instincts evolved among bounded objects. Gravity makes spheres where spheres are the natural local compromise of matter under pressure. That is all. It does not announce the totality of existence in that same form. It does not elevate the shape of a planet into the geometry of everything. It lets the local and the global diverge because there is no reason they should be the same category of fact. Once that is accepted fully, the opening contradiction does not merely disappear, it inverts. The roundness of ordinary things no longer makes flatness surprising. It makes our old way of thinking look narrow. Because now the real surprise is this. We ever expected local objects to dictate the metric structure of the whole. We ever believed that what matter does in a gravitational well could answer the large-scale geometry of an expanding universe. We ever mistook the comfort of a picture for the authority of a measurement. That inversion is one of the quiet pleasures of deep understanding. The problem does not get solved in the way the mind first demanded. The mind itself gets corrected. The entire frame in which the problem was posed becomes obsolete. And that is when a topic stops being educational content and becomes something more unsettling. It becomes a revision of what counts as obvious. The most powerful scientific ideas do not merely add information. They redraw the border between intuition and reality. They teach us that some of the things that feel nearest to certainty are nearest only in perception, not in law. The flatness of the observable universe belongs to that class of ideas. It does not ask us to memorize one more fact about cosmology. It asks us to surrender a visual instinct that once felt almost self-evident. And surrender is the right word. Because nothing in this process feels like a natural extension of common sense. Common sense wants an outside. It wants a whole that can be pictured. It wants shape to mean contour. It wants gravity to apply with the same visual logic everywhere. It wants the universe to be one more object, simply larger. Cosmology keeps removing each of those supports. No outside view guaranteed. No complete silhouette guaranteed. No direct equivalence between local shape and global geometry. No promise that the whole will fit inside the categories that evolved for middle-sized life on one planet. What replaces those comforts is not chaos. It is discipline. A discipline so exact that it can read the geometry of the cosmos from a temperature pattern in ancient light. A discipline so severe that it can distinguish local curvature around massive objects from the average spatial curvature of the universe itself. A discipline so patient that it can admit the limits of the observable horizon without collapsing into vagueness. A discipline that knows when to stop speaking, not because truth has vanished, but because evidence has reached the edge of what our patch of reality can honestly provide. That edge matters more than most people realize. Because it means cosmology is not a fantasy of total vision. It is the science of internal legibility under constraint. We do not know everything because we are not nowhere. We are somewhere, late, local, moving through a universe that permits certain measurements and denies others. The power of the subject comes from how much can still be known from that position. You can almost feel the austerity of it. Here we are, on a small world that became round for ordinary gravitational reasons, orbiting a star that did the same, inside a galaxy whose local history is messy and contingent, inside a visible cosmic web whose structure grew from tiny primordial irregularities. And yet, from this late local vantage point, we can still infer that the large-scale spatial geometry of the observable universe is astonishingly close to flat. That should not feel like familiarity. It should feel like access. A narrow, rigorous access to something far deeper than the things we first trusted. And access changes how the night sky looks. Not visually at first. The stars do not rearrange themselves to reward the insight. The moon does not stop being beautiful because it has lost its authority over the question. The horizon does not shimmer with labels. But the hierarchy beneath perception changes. You stop seeing the sky as a cabinet of objects and start seeing it as local brightness suspended inside a much older order. You understand that every round thing above you is a late solution to local physics, while the geometry that permitted those solutions was written far earlier into the expanding structure of space. The objects did not create the stage permitted the objects. That is the reversal this topic was always moving toward. And once it arrives, even the word flat acquires a different emotional weight. It no longer sounds plain, it sounds ancient, hard-won, almost severe in its understatement. The observable universe is nearly flat, a quiet sentence hiding a violent early history, a delicate critical balance, an inflationary mechanism, a microwave background standard ruler, a horizon that limits certainty, and a deep correction to the way human intuition mistakes object shape for cosmic truth. Few scientific statements sound so modest while carrying so much buried architecture, which is why the answer to the original question is now both simpler and stranger than it first appeared. The universe is not flat when everything else is round. The universe is nearly flat on large scales, because large-scale geometry is not the same kind of thing as the local roundness gravity produces in stars, planets, and black holes. Local objects become spherical because matter can settle under force. The observable cosmos is near flat because the relation between density and expansion, almost certainly shaped by an inflationary past, leaves large-scale spatial curvature extraordinarily close to zero. These are not conflicting facts. They are facts from different levels of reality. Once separated, they do not compete. They illuminate each other. And perhaps that is the deepest residue the subject leaves behind. Not awe in the soft sense, not even dread, something colder and cleaner. The recognition that reality can be lawful without being picturable, measurable without becoming possessible, intelligible without becoming familiar. We live inside a universe whose local contents can curve, collapse, ignite, merge, and round themselves into worlds. And yet the space between those worlds, the deeper arena itself, remains so nearly flat that the oldest light in existence still carries that verdict to us across billions of years. Gravity made the worlds round. It did not make the universe into one. And that is where the question finally stops being about shape. Because once the geometry of the observable universe has been separated from the shapes of the objects inside it, something more interesting comes into view. The real subject was never visual form. It was hierarchy. What is fundamental, and what is downstream? What writes the rules, and what merely inherits them? The moon inherits them, stars inherit them, galaxies inherit them, black holes, for all their violence, inherit them. Even the cosmic web inherits them. None of those structures decides the large-scale geometry of the universe after the fact. They unfold within a background whose essential terms were set long before they existed. That is why the script has kept moving backward, away from visible things, away from familiar scales, away from the objects that first seduced intuition, toward the early universe, where the deeper order had not yet been hidden beneath complexity. And what emerges there is one of the strangest reversals in all of science. The universe did not start complicated and become simple. It started simple enough for geometry to dominate. Then complexity bloomed inside that simplicity. That is not how human thought usually imagines creation. We expect richness to come first, or at least to feel fundamental. We are drawn to the ornate, the differentiated, the visible. But cosmology points in the other direction. The early universe, on the largest scales, was astonishingly uniform. Its perturbations were tiny. Its geometry was already disciplined. Its expansion was already underway. The future stars, planets, and living bodies were not yet written as objects. They were latent in slight statistical differences, hidden in almost absurd smoothness. The visible world we love is an elaboration. The deep order beneath it is older and quieter. That is why flatness, once understood properly, begins to feel less like a fact among facts and more like a clue about reality's operating style. The universe does not build from the categories the eye prefers. It builds from dynamical laws, geometric conditions, and early boundary relations that only later harden into things. Things feel primary because they are what organisms like us evolved to notice. But cosmology keeps stripping that priority away. A planet is not fundamental because it is round. A star is not fundamental because it is bright. A galaxy is not fundamental because it is large. Even a black hole is not fundamental because it is extreme. Those are all local achievements. The geometry of space-time, the expansion of the universe, the relation between energy density and curvature, the primordial conditions from which all structure emerged. These are closer to the base layer, less visible, more austere, more difficult to love at first, and yet more explanatory of everything that arrives afterward. This is the point at which the phrase, "the universe is flat," acquires a kind of philosophical sharpness that ordinary summaries rarely capture. Not because it tells us everything, it does not, but because it tells us what sort of answer reality is willing to give. Reality, at this depth, does not answer in silhouettes. It answers in relations. It answers in measured angular scales, density parameters, inflationary consequences, horizon limits, background metrics. It answers structurally. And structure is easy to underestimate because it does not dazzle the eye in the same way objects do. A star dazzles. A nebula dazzles. A spiral galaxy seen face-on dazzles. Flatness does not dazzle. It does something more difficult. It quietly governs the arena in which dazzling things can appear at all. There is a severe beauty in that, a beauty that does not announce itself with spectacle. The universe becomes less like a museum of strange objects and more like an exact language whose visible nouns are generated by invisible grammar. The nouns are what we admire first. The grammar is what actually organizes the sentence. And grammar almost always feels less exciting until you realize it decides everything. That is why the original intuition was not merely incomplete, it was inverted. It treated the visible nouns as the authority and tried to infer the grammar from them. It looked at round things and assumed reality must be round in the same way. But the grammar came earlier. The metric came earlier. The large-scale energy curvature relation came earlier. Inflation, if the broad picture is right, came earlier. The visible objects were never the legislators. They were the consequences. Once you see that clearly, another subtle misconception falls away. People often imagine that, because general relativity says matter and energy curve space-time, the universe should somehow grow more globally curved as it fills with structure, more stars, more galaxies, more black holes, more curvature, therefore a less flat universe. That intuition is understandable, but it quietly mixes local geometry with the average large-scale description again. Structure formation does not rewrite the large-scale global geometry in the simplistic way the image suggests. Yes, matter curves space-time locally. Yes, dense objects produce real gravitational effects, strong enough in some regions to bend light, distort time, and trap escape entirely. But the cosmological statement about flatness is not canceled by the existence of those local wells. The Friedman-style large-scale description is an averaged one. It asks what the universe looks like when viewed across scales vast enough that local drama becomes texture rather than law. In that smooth description, the observable cosmos still comes out astonishingly close to spatially flat. This is not hand-waving. It is one of the discipline points that keeps the whole framework coherent. You do not infer the global geometry by adding up the visual violence of local regions. You infer it by measuring the large-scale metric behavior of the universe as a whole, how light travels across the background, how standard rulers project onto the sky, how expansion and total energy density interrelate. A black hole is real, a galaxy cluster is real, a filament of the cosmic web is real. None of them, by their mere existence, overturns the near-flat large-scale result. Reality permits deep local wounds inside broad global balance. That sentence should linger, because it carries more than one truth at once. It is true about geometry, but it is also true about how the universe seems to be built. The cosmos is not cleanly simple or messily complicated. It is both, depending on the level of description. On one scale, it is nearly homogeneous. On another, it is webbed with structure. In one regime, Euclidean geometry survives with extraordinary success. In another, space-time bends around masses into strange local configurations. The deepest mistake is not choosing the wrong one. It is failing to respect the difference of scale. And scale is one of the most pitiless teachers in science. At human scale, a table looks flat. At planetary scale, Earth is curved. At mountain scale, Earth is rough. At atomic scale, solidity dissolves. Each level is real. None authorizes all the others. The crime against understanding begins when one scale is promoted into a universal template. That is exactly what the opening question did. It took local rounded objects and promoted their shape logic into a statement about the entire cosmos. Flatness matters because it punishes that move. It tells us that the universe is under no obligation to preserve the visual habits formed in its small corners. It tells us that what seems self-evident at one scale may be almost meaningless at another. It tells us that the eye, left unattended, turns local truth into cosmological error. By now, the old question has almost become useful precisely because it was wrong. It reveals the natural path by which intuition misfires. First, it notices a real pattern. Gravity tends to make sufficiently massive objects round. Then, it silently universalizes the pattern. Then it stumbles over cosmological flatness and imagines a paradox. The paradox survives only until the categories are cleaned, the scales are separated, the measurement is understood, and the early universe mechanism is brought into view. After that, what remains is not contradiction but a more difficult kind of coherence. Local gravity sculpts matter into stars, planets, and black holes. Large-scale cosmology describes an expanding universe whose observable geometry is near-flat. Inflation explains why the near-flatness is not absurdly fine-tuned. The cosmic microwave background records the evidence. The horizon limits how far the claim can honestly be pushed. Everything locks together, but it locks together at a cost. The cost is that reality becomes less picturable. That is the trade cosmology repeatedly forces upon us. More precision, less comfort, more evidence, less intuitive closure, more law, less familiar imagery. Yet, there is something strangely dignifying in that trade as well. It means the universe is not shallow enough to be exhausted by its first appearance. It means knowledge is not merely confirmation of instinct, but the disciplined correction of it. And perhaps that is why the flatness story remains so compelling even after the technical answer is in hand. Because the answer does not merely resolve a puzzle about cosmology, it reveals something about the human position in reality. We are creatures of local evidence trying to understand global structure, creatures of surfaces trying to understand metrics, creatures who trust contours trying to understand curvature from within. The fact that such creatures can infer as much as we have is extraordinary. The fact that our first instincts were so wrong is less an embarrassment than a condition of the journey. The universe was never going to be built for immediate transparency to primates from one planet. The remarkable thing is not that intuition failed. It is that measurement, theory, and patience can reach beyond it at all. The remarkable thing is that an animal who first trusted the roundness of the moon can end by understanding that the observable cosmos is near flat for reasons bound up with critical density. inflationary dynamics, and the fossil geometry of ancient light. That is a genuine change in the way reality becomes visible. Not to the eye, to the mind trained against its own first impulses. And once that shift has happened, the familiar sky is no longer merely familiar. Every round world becomes, in a quiet way, less metaphysically authoritative than it looked. Beautiful, still, real, still, but no longer foundational. Foundational lies deeper in the background laws that made such worlds possible. The spheres were late. The flatness was older. And the mind that once confused the two has had to learn, slowly and almost against itself, that the universe was never the kind of thing that needed to become round. Because to become round is already the wrong kind of verb. It implies a body settling into a shape, a finite thing responding to forces within a larger setting. It implies boundary, center, exterior relation, and that entire grammar has been stripped away now. By this point, the universe cannot honestly be imagined as one more candidate for spherical completion. That was the first illusion. What remains is stranger, cleaner, and much less forgiving. The universe does not sit there deciding between shapes the way a drop of water does. The universe, in the cosmological sense, is the evolving geometry within which such drops, planets, stars, and galaxies can ever exist. Its near flatness is not the unfinished absence of roundness. It is not a cosmic object that failed to close. It is the large-scale metric condition of the observable arena, tied to density, expansion, and the early history of space-time itself. Once that lands fully, even the emotional texture of the question changes. At the start, the topic felt like a visual puzzle, something almost playful. Why is one thing this way when so many other things are that way? But the more honestly the subject is opened, the more the playfulness drains out of it. In its place comes something colder. The recognition that human intuition repeatedly mistakes the products of local dynamics for the architecture of the whole. And it does so because local life makes that mistake almost inevitable. We live among objects. We handle bounded things. We learn the world through surfaces, edges, contours, mass, and motion. We do not grow up drawing giant triangles across cosmic space, or fitting acoustic peaks in relic radiation. So, the mind begins with the wrong authorities. It takes the moon seriously. It takes the horizon seriously. It takes the sphere seriously. It builds a universe out of what it can see and touch, then feels betrayed when deeper physics refuses to match. But betrayal is not quite the right word. Correction is, the universe is not mocking intuition. It is simply under no obligation to preserve it beyond the scales where it was forged. And that may be the most important pattern in the whole story. Again and again, reality turns out to be lawful in ways that local perception did not predict. Not chaotic, not irrational, not mystical, lawful, but on terms larger, harsher, and less picture-friendly than immediate experience led us to expect. Flatness belongs to that class of revelations. It is not emotionally loud. It does not strike the senses the way a supernova image does, or the way a black hole does in the imagination. It arrives quietly, almost embarrassingly quietly. A statement about spatial curvature, a constraint on a parameter, a feature in the microwave background, but inside that quiet statement is one of the most radical revisions the mind can undergo. The visible world is not the authority it first appears to be. That line should not be rushed past, because it reaches beyond this one topic. It says something general about science at its most serious. The eye is not the enemy, but it is not the judge either. Sight gives us the local theater. Measurement and theory uncover the stage. The two can be related, but they are not equal. The sky of visible things is not false. It is derivative. A round planet is derivative. A round star is derivative. A black hole is derivative. Even the web of galaxies, for all its grandeur, is derivative. Derivative not in the sense of unimportant, but in the sense of coming later, generated within prior conditions that are less obvious and more fundamental. Once that ordering is clear, the opening problem dissolves so completely that it almost becomes difficult to remember why it felt compelling in the first place. Why should the universe be round because planets are? Why should global spatial curvature answer to the equilibrium shape of self-gravitating matter? Why should a metric property of the observable cosmos be visually homologous to an object sitting in it? The more exact the categories become, the more impossible the old confusion starts to look. And yet it mattered that the confusion felt natural, because that naturalness tells us something sobering about how knowledge works. We do not begin by asking the right question. We begin by asking the nearest wrong one. Then, if the inquiry is disciplined enough, the wrongness of the question reveals the hidden structure of the right answer. The Flatness story is beautiful in exactly that severe way. A child's visual objection becomes a doorway into intrinsic curvature, critical density, inflation, horizon limits, and the distinction between local collapse and global geometry. The bad question was not useless. It was diagnostic. It exposed the fault line between perception and physics. And once that fault line is exposed, another deep implication comes into view. The universe is not merely stranger than intuition guessed. It is structured in layers that do not naturally collapse into one another. Local truth remains true. Gravity does make large, relaxed objects approximately spherical. That did not become false. But local truth is no longer allowed to legislate global truth. The moon keeps its roundness. It loses its jurisdiction. That is a powerful kind of intellectual maturity, learning not just what is true, but where it is true, learning the domain of a fact, the scale at which it applies, the regime beyond which it begins to mislead. Most errors in deep science are not born from total nonsense. They are born from overextended truths. An idea works beautifully in one setting and is then promoted too far. Flatness and roundness only looked contradictory because one real pattern was extended into the wrong domain. Gravity rounds worlds. True, therefore the universe should be round. False. The first sentence survives. The second collapses. And once it collapses, the universe becomes more coherent than before, but also less domesticated. Because the corrected picture is not more visually satisfying, it is less so. The reward is not a prettier image. It is a more exact relation between different layers of reality. Geometry where geometry belongs. Objects where objects belong. Inflation where early universe mechanism belongs. Measurement where human certainty deserves to be earned. That is why the topic has this peculiar emotional afterimage. It is not just informative, it is disciplinary. It trains the mind away from one of its favorite habits, mistaking what is vivid for what is fundamental. Vivid is not fundamental. Nearby is not fundamental. Picturable is not fundamental. Late is not fundamental. The most fundamental layer available to us here is something colder, the large-scale behavior of space. The relation between its geometry and its energy content. The way ancient light carries evidence across time. The way inflation may have reset the visible universe before anything familiar had formed. Those are not the facts that come first to intuition. They are the facts that survive after intuition has been corrected. And that correction does something almost philosophical to the sense of reality. It inverts our trust. We begin by trusting what the eye can certify. Spheres, surfaces, local regularities. We end by trusting what only a disciplined chain of inference can certify, near flat spatial geometry on the largest observable scales, constrained by relic radiation and the dynamics of cosmic expansion. The first trust feels natural, the second is earned, but once earned, it carries more authority. That is one of the reasons science can feel spiritually harsher than myth, while also being more transformative. Myth often preserves the scale of intuition and enlarges its symbols. Science, at its deepest, often breaks those symbols. It does not say the sphere is sacred, and therefore the universe must be a sphere. It says the sphere is a local physical outcome, and the universe owes it no metaphysical promotion. That is less flattering to human imagination. It is also more profound, because it leaves reality lawful on its own terms rather than ours. Which means the final residue of this topic is not really about flatness or roundness alone. It is about category discipline. About learning that the world is intelligible only when we stop forcing one level of truth to answer for another. About accepting that some statements belong to local matter, some to large-scale geometry, some to early universe dynamics, some to observational limits. And that clarity begins when those statements are no longer shoved into the same conceptual box, just because language makes them sound similar. The moon is round. The observable universe is nearly flat. These are not competing descriptions. They are descriptions from different layers of the same lawful reality. And once that becomes fully visible, the stars overhead lose none of their beauty. But they gain a different kind of severity. Their shapes no longer feel like hints about the form of the whole. They feel like local consequences, exquisite, luminous, temporary, suspended inside a geometry that was already there before any star ignited. The sky becomes less like a gallery of cosmic answers and more like a late display inside a much older order. That older order is what the eye missed. That older order is what the microwave background preserved. That older order is what inflation may have helped impose upon the observable patch. That older order is why the opening contradiction could never survive contact with real cosmology. By now, the answer is almost simple enough to say in a single breath, but only because the path to simplicity was so long. Everything else is not round in the relevant sense. Only certain local objects made of matter become approximately round under self-gravity or related physical pressures. The universe, meanwhile, is not an object in a larger space, but the large-scale space-time arena itself. Its flatness refers to spatial geometry on cosmic scales, how distances, angles, and light propagation behave, and observations show that this geometry is extremely close to flat within the observable domain. That near flatness is intimately tied to the universe's total energy density and is naturally explained, in the standard picture, by an early epoch of inflation that diluted any detectable primordial curvature. No paradox, no contradiction, only a mistaken category, corrected by physics. But the emotional consequence of that correction is larger than the tidy summary makes it sound, because once you understand it, you no longer look at the night sky the same way. The visible things remain what they are, but they stop pretending to be authorities on the deepest structure of reality. Their roundness becomes local, almost provincial, beautiful, but not foundational. Foundational belongs to the geometry between them, the ancient balance beneath them, the conditions written into the universe before they had any form at all. The universe is not nearly flat because gravity failed to make it round. It is nearly flat because gravity making things round was never the relevant question. Because the relevant question was always older than the objects that confused us. Older than planets, older than stars, older than galaxies, older than the first atom. By the time anything in the universe had a chance to become round, the large-scale geometry of the observable cosmos had already been set on its path. The relation between expansion and density was already doing its work. If inflation occurred, the violent stretching that would render our patch so nearly flat had already happened in the first instance that physics can even begin to discuss responsibly. The things we see now are not the authors of that geometry. They are descendants of it. That is the final inversion. At the beginning, visible objects looked like the evidence. By the end, they look like late consequences. The true evidence came from something far more austere, a temperature map in ancient light, the logic of general relativity, the behavior of primordial sound waves, the extraordinary closeness of the density parameter to the critical case. The eye wanted moons and spheres. Reality answered with acoustic peaks and space-time metrics. And that answer does something subtle to the sense of existence itself. It shifts the center of gravity away from objects and toward conditions, away from forms and toward the hidden permissions that let forms arise. We usually think of reality as built from things. Cosmology keeps suggesting that reality is built, more deeply, from relations and laws within which things briefly happen. That may sound abstract until you feel how much it changes. A round planet no longer feels like a clue to the universe's own shape. It feels like a local event allowed by deeper rules. A star no longer feels like a miniature model of cosmic order. It feels like a temporary concentration of matter inside a geometry that preceded it. Even a black hole, which once seemed like the ultimate gravitational object, becomes one more local drama occurring within a large-scale background that does not answer to its intensity. The local remains real. It loses primacy. And once primacy moves, the whole sky acquires a different weight. The stars overhead are still stars. They still burn, explode, collapse, merge, and round themselves under pressure. But they cease to feel like the dominant layer of reality. They become almost like bright interruptions in a deeper order, not illusions, not decorations. Interruptions, local eruptions of complexity in a universe whose oldest large-scale condition was smoothness, near flatness, and astonishing geometric discipline. That is what makes the subject linger. It reveals a hidden asymmetry in how we habitually think. We treat the visible as basic and the invisible as derived. Cosmology often tells the reverse story. The invisible geometric structure is more basic. The visible objects are what happen inside it. Once that lands, even the phrase flat universe stops sounding like a conclusion and starts sounding like a compressed summary of an entire worldview. It contains, folded inside itself, the claim that the large-scale spatial geometry of the observable universe is very nearly Euclidean. It contains the claim that this is not a visual statement about outline or outer surface. It contains the claim that local gravitationally rounded objects say almost nothing about the issue. It contains the claim that the early universe was balanced in a way that, without inflation, would look alarmingly fine-tuned. It contains the possibility that inflation stretched our visible patch so violently that any primordial curvature became almost undetectable. It contains the horizon limit that keeps us honest about what the universe can mean observationally. It is a small sentence carrying a massive burden. And perhaps that is why it can feel so philosophically sharp. The sentence does not merely correct a misconception about cosmology, it trains the mind against a much broader temptation. The temptation to think that what is vivid to human perception must also be metaphysically central. That temptation appears everywhere. We think solidity is central because things feel solid. We think simultaneity is central because experience feels shared. We think visual shape is central because form arrives so immediately to the eye. Then physics keeps removing those privileges, one by one. Matter becomes mostly field and structure. Time becomes local and relational. Space becomes dynamic. Shape becomes metric instead of outline. And the universe, which seemed as though it should be one giant object among objects, becomes an internally measured geometry, whose deepest features were never visible in the way we first demanded. The lesson is not that human intuition is useless. The lesson is that intuition is local. It is exquisitely good at the scales that made us, badly overconfident beyond them. The moon's roundness was real evidence about the moon. The mistake was promoting it into evidence about the geometry of all existence. Once you see that error clearly, you begin to notice how often understanding depends on preventing local truths from colonizing larger domains. That is what happened here. Hydrostatic equilibrium colonized cosmology. Object shape colonized geometry. Visual form colonized metric structure. A real local pattern became a false global expectation. And then the universe refused it. Not with chaos, not with arbitrariness, with a better law. A law stating that local matter can relax into near spheres while the large-scale observable universe remains nearly flat. A law stating that geometry and density are linked by relativity. A law stating that ancient light can carry evidence of that geometry across cosmic time. A law stating that violent early expansion can dilute curvature before stars or planets ever form. A law stating that the visible order of local things is not the same as the foundational order of the whole. This is where the script's central illusion fully dies. The universe is not flat instead of being round, as though the cosmos rejected one available shape and selected another. The universe is nearly flat in the large-scale cosmological sense, because large-scale cosmological geometry is not the same category of fact as the roundness of local gravitational bodies. There was never a competition. There was only a confusion between levels. Once levels are cleaned apart, the contradiction vanishes so completely that the original wording begins to feel almost impossible to inhabit again. Why is the universe flat when everything else is round? Because everything else was a mistake. It bundled together planets, stars, droplets, and black holes, local bounded systems, and quietly treated them as though they exhausted the forms reality knows how to take. But the universe, in the relevant scientific sense, is not one more bounded system of that kind. It is the evolving space-time framework in which all bounded systems arise. To ask why it does not share their equilibrium shape is like asking why the grammar of a language is not itself one of the nouns it governs. It is the wrong layer entirely, and that wrongness is productive because it leaves behind a deeper insight than a mere correction. Reality is layered. The layers do not answer to one another symmetrically. The visible is often downstream of the invisible. The late is often explained by the early. The objects we trust are often local expressions of conditions they did not write. That is the mature form of the answer. Not a fact about one topic, but a revised way of seeing how topics fit together. Cosmology, at its best, does not just tell us what the universe is like, it teaches us what kind of mistake a mind like ours is most likely to make when it first confronts totality. We objectify it. We localize it. We imagine it from outside. We ask it to resemble the things that fill our days. Then the evidence slowly, almost sternly, removes those habits. By the end, the universe has not become less beautiful. It has become less accommodating. Its beauty no longer lies in matching our first images. It lies in the consistency with which it escapes them. It lies in a deeper order that is lawful enough to infer, disciplined enough to measure, and indifferent enough to leave our intuitions behind. That is why the answer feels more like a shift in perception than a solved fact. The moon is still round. The earth is still round. Stars are still round. Black holes still drive space-time toward stark local simplicity. But now those facts no longer point upward toward the shape of the universe. They point downward, toward local physics. They become what they always were, regional truths inside a larger geometry. And that larger geometry, in the observable cosmos, is so nearly flat that the oldest light in existence still carries its verdict, a faint whisper from the early universe, telling us that by the time the first round worlds would someday emerge, the deeper stage had already chosen its discipline. The worlds became spheres because matter could fall. The universe became nearly flat because geometry, density, and an ancient expansion history made that the large-scale rule of the visible cosmos. Those are not rival answers. They are different depths of the same reality, and the deeper one came first, and that may be the strangest part of all. Not that the observable universe is nearly flat. By now that has become intellectually legible. Not that local objects become round. That was never in doubt. Not even that inflation offers a powerful reason why our visible patch should look so geometrically disciplined. The strangest part is how close to perfect the balance appears to be, and how easily that fact can be spoken without sounding like anything at all. The observable universe is extremely close to flat. A sentence so quiet it almost hides its own violence. Because inside that sentence sits an entire chain of improbabilities and mechanisms. It contains the old flatness problem, in which even a tiny early departure from the critical case should have grown across cosmic history into obvious curvature. It contains the inflationary rescue, where rapid expansion drives observable space toward the flat limit. It contains the cosmic microwave background, whose ancient ruler lets geometry reveal itself through angle. It contains the admission that our horizon is finite and our confidence must be local, not godlike. And above all, it contains a kind of cosmic austerity. Reality, for all its later richness, appears to have begun in a state of extraordinary large-scale discipline. That discipline is easy to miss because the present universe is so busy. Busy with stars, busy with galaxies, busy with collisions, jets, accretion disks, supernovae, magnetized gas, clustering, lensing, collapse, and drift. The visible cosmos performs turbulence so well that it becomes hard to feel how simple its broadest geometry still is. But simplicity is exactly what the data keep forcing on us at the largest scales. Average over enough distance, smooth over enough structure, and the universe becomes almost unnervingly well-behaved, nearly homogeneous, nearly isotropic, nearly flat. The objects scream. the background barely raises its voice. And yet the background is older. That contrast is one of the deepest emotional truths in cosmology. Late reality feels dramatic. Early reality sets the terms. By the time the first stars ignite, the geometry is already in place. By the time galaxies braid themselves into filaments, the key balance between expansion and density is already ancient. By the time planets cool into spheres, the question that first misled us has already been answered by the universe's earliest conditions. We keep arriving late to decisions that were made before visibility itself had matured. That is why near flatness has a special kind of severity. It is not merely one feature among others. It is a sign that the observable cosmos carries the memory of an early calibration so exact that later structure could bloom without overthrowing the background rule. The more exuberant the local universe becomes, the more astonishing that background restraint starts to feel. And restraint is the right word. The universe is not maximally curved. It is not flagrantly closed. It is not obviously open. It rides an astonishingly narrow middle path. That middle path is what makes the result feel almost too elegant. Not because elegance itself is suspicious. Nature often has that quality when described by the right equations. But because elegance here is dynamically hard-won. Without inflation, it looks painfully fine-tuned. With inflation, it looks like the relic of an overwhelming event that punished detectable curvature until almost none remained within our horizon. Either way, the visible cosmos ends up living unnaturally close to the middle. A knife edge is not visually dramatic from far away. It becomes dramatic when you understand what it means to remain there. This is why the language of flatness can be so deceptive. To non-specialists, it can sound disappointingly plain, as though modern cosmology investigated the shape of the universe and discovered something almost boring. But flatness, in this setting, is not boring at all. It is one of those rare results whose conceptual quietness is exactly what makes it unsettling. The universe did not announce its geometry with some flamboyant global curve obvious to the eye. It hid the answer in ancient light, in the behavior of angles, in the background relation between density and expansion. It made us earn the simplicity. And simplicity earned this way feels different from simplicity assumed. Assumed simplicity is innocence. Earned simplicity is revelation. By the time you arrive at near flat, you have already passed through enough theoretical and observational pressure that the word no longer sounds casual. It sounds compressed, like a small label attached to a very deep mechanism. It becomes impossible to hear without also hearing the unspoken structure behind it. The Friedmann equations, the critical density, the flatness problem, the inflationary epoch, the acoustic horizon, the microwave sky, the horizon limit. The sentence stays short. The reality inside it keeps expanding. There is also a darker edge to this. Because the better the observable universe fits the near-flat case, the more successfully inflation, if inflation is the right broad framework, has erased direct access to whatever curvature may have existed before. In that sense, the clarity of our result may be tied to a deeper loss. We can say with increasing precision that our visible patch is nearly flat. That very success may be the consequence of an early episode that pushed other possible signatures far beyond our reach. Knowledge and erasure, here, may be intertwined. We learn that the observable cosmos is flat because something in the early universe may have stripped away the local visibility of alternatives. The answer becomes clearer. The deeper prehistory becomes harder to recover. That is one of the crueler patterns in fundamental physics. Some mechanisms explain the present by making the past less accessible in detail. Inflation, if broadly right, may have done exactly that. It turns flatness into a natural consequence while also stretching earlier conditions beyond observational intimacy. The universe becomes legible by making itself forgettable. That is not total forgetfulness. Quantum fluctuations, stretched by inflation, may survive as the seeds of later structure. The microwave background still carries their trace. So, the early universe did not vanish without residue. But the large-scale curvature that would once have dominated the opening question is precisely the sort of thing inflation was built to suppress. The geometry we can read now may therefore be the geometry of aftermath rather than origin. and aftermath has its own emotional force. It means the calmness of the observable universe may not be primordial in the innocent sense. It may be the polished remainder of something brutal. Near flatness then ceases to be merely a property and becomes a scar pattern, not visible as injury, but as overcorrection. Space appears disciplined because it was driven there. The later universe inherits a rule written by violence so early and so complete that almost all ordinary objects are born after the decisive act has disappeared from sight. The first spheres arrive after the flattening. That line matters because it finally seals the reversal the whole script has been building toward. At the beginning, round worlds looked like the primary fact. Flatness looked like the anomaly. Now, the order is completely reversed. Large-scale near flatness belongs to the deep background history of the observable cosmos. Round worlds are late local products of gravity operating within that background. The anomaly was never flatness. The anomaly was the human expectation that local shape had any authority over the whole. By now, that expectation should feel almost impossible to reconstruct without effort. And yet there is one more reason the subject lingers, even after all this. The universe refuses total closure. We have strong evidence for near flatness within the observable domain. We have a powerful framework explaining why. But we do not possess a final outside view. We do not know, in the strongest imaginable sense, the ultimate total geometry of everything beyond our horizon. The observable universe may be one almost level patch of a far larger whole, or the whole may itself be truly flat, or topology may complicate what simple curvature language alone can say. The data constrain, they do not deify us. That incompleteness is not a flaw in the subject, it is part of its tone. Near flatness is therefore both a triumph and a limit. A triumph because ancient light, relativity, and cosmological measurement have carried us astonishingly far from naive intuition. A limit because the horizon remains real, and because the very mechanism that explains flatness may have hidden more original conditions than it revealed. The universe lets us know enough to correct ourselves. It does not necessarily let us finish the picture. And perhaps that is why the result leaves behind not simple awe, but something tighter, a kind of haunting clarity. The night sky no longer feels like a set of shapes from which the whole can be guessed. It feels like late local weather inside a background whose broad discipline was established before weather existed. The visible universe is rich. The deeper rule beneath it is spare. The objects are loud. The geometry is quiet. And the quiet part, somehow, is closer to the truth. Which means the strangest thing about the universe being nearly flat is not that it contradicts the roundness of stars and planets. It is that it never had to answer to them at all. The worlds became round because matter, given gravity and time, can settle. The observable cosmos became nearly flat because the geometry of space, the balance of density and expansion, and a violent early history imposed a different kind of order long before any world existed to confuse the issue. The deeper answer was already there. The visible question arrived later. And that is why the night sky does not look the same once the question has been answered properly. Not because anything visible changes. The moon is still round, Jupiter still swells at the equator, stars still hold themselves in near spherical tension, black holes still turn collapse into the most severe local geometry nature allows, galaxies still braid themselves into luminous structure across the dark. All of that remains. What changes is the order of trust. At the beginning, the eye trusted the objects first and tried to build the universe out of them. It took the rounded things of the world as clues to the shape of reality itself. That was the instinctive move, natural, immediate, and wrong in exactly the way deep questions are often first answered wrongly, by extending a local truth until it breaks. Because those objects were never the deepest layer. They were the late arrivals. Planets are late, stars are late, galaxies are late. Even the great visible web of matter is late. By the time anything in the universe had become round enough to persuade a human eye, the more important work had already been done. The large-scale geometry of the observable cosmos had already been disciplined. The relation between density and expansion had already narrowed the possibilities. The oldest light had already begun carrying its silent record forward. If inflation belongs to the true history of the early universe, then the decisive flattening of our visible patch happened before any familiar object existed to inherit it. The stage was already set, and once that becomes real in the mind, the original question matures into its final form. It was never asking about shape. It was asking whether the visible world is fundamental. The answer is no. The visible world is real, but it is not fundamental in the way intuition first hopes. It is derivative, a later flowering, a set of local consequences unfolding inside deeper conditions that do not announce themselves through ordinary appearance. The moon does not explain the universe. The universe explains why moons can exist. A star does not reveal the geometry of the whole. It reveals what matter does under local gravity inside a geometry it did not write. That reversal is the true destination of the story, not a fact to memorize, a hierarchy to accept. The universe is not nearly flat because gravity somehow failed to make it round. The universe is nearly flat within the observable domain because large-scale geometry is a different layer of reality than the local equilibrium shapes gravity produces in bounded systems. Those local systems, worlds, stars, black holes, are sculpted by matter falling inward, pressure balancing outward, rotation adding slight asymmetry, collapse erasing roughness. They become approximately round because they are objects with centers, boundaries, and material that can settle. The universe, in the relevant cosmological sense, is not an object of that kind. It is not sitting in a larger room, waiting to reveal its contour from the outside. It is not a celestial sphere whose edge we have failed to step far enough back to see. It is the space-time arena itself, measured from within, whose large-scale spatial geometry appears astonishingly close to flat. That result is written into the way ancient light reaches us, into the way primordial sound waves project onto the sky, into the relation between total energy density and critical balance, into the violent early history that may have driven our visible patch so close to Euclidean simplicity that any primordial curvature now lies almost beyond detection. Gravity made the worlds round. It did not make the universe into a world. That is the cleanest version of the answer, and by the end, it should feel less like a clever line than like a corrected way of seeing. Because what this topic finally exposes is not just a misunderstanding about cosmology, but a recurring weakness in human intuition. We trust what is vivid. We trust what is bounded. We trust what can be pictured. Then physics keeps forcing the same harsh lesson. Vivid is not fundamental. Bounded is not fundamental. Pictured is not fundamental. The deepest structure of reality often arrives not as an image, but as a relation. Not as an object, but as a rule. Not as something the eye can complete, but as something measurement can constrain. The universe is lawful in that colder way. And there is something haunting in the thought that the visible heavens, all the round worlds, all the burning stars, all the bright local dramas we are tempted to elevate into cosmic truths, are suspended inside a background whose decisive order was established before any of them existed. The objects are young compared with the conditions that made them possible. The things that feel substantial to us are, in a deeper sense, downstream from geometry. The spheres were never the argument. They were the after effect, which is why the answer, at the end, feels both simpler and less comforting than the question promised. There is no grand visual payoff in which the universe suddenly reveals itself as a hidden sphere, or a sheet, or a dome. There is only the more disciplined truth that the observable cosmos is nearly flat on the largest scales we can test, that this flatness belongs to the geometry of space rather than the contour of an object, that local roundness belongs to matter settling under gravity within that geometry, and that the whole apparent contradiction existed only because the mind confused one level of reality for another. Once that confusion is gone, the sky becomes stranger in a quieter way. The moon is still beautiful, but it is no longer evidence. The stars are still luminous, but they are no longer authorities. Their shapes remain what they are, local, real, temporary. The deeper order lies between them, beneath them, before them. And perhaps that is the final shift in perception this question was always capable of delivering. The universe does not become meaningful when it resembles the things we already know. It becomes meaningful when we finally stop asking it to. So, why is the universe flat when everything else is round? Because everything else was never everything else. Because roundness is what matter does locally when gravity gives it somewhere to fall. Because flatness is what large-scale space appears to be when ancient light, critical balance, and a violent early expansion history have finished speaking. Because the worlds are objects, and the universe was never that kind of thing. Look back at the moon now, and it no longer points outward toward the shape of the whole. It points inward toward the small, local physics of collapse, pressure, and equilibrium. The larger truth is quieter than that, older than that, written into the space around the moon long before the moon existed. And that may be the most unsettling realization of all. The rounded things we love are not models of reality's deepest form. They are brief, local ornaments, inside a universe whose truest large-scale shape was never waiting to be seen, only measured, from within,